Oh, 9 a.m. Pacific. I see that we have people from all over the place. Michigan and India, and Nigeria, Atlanta, all kinds of places. So welcome to Southern Data Science Conference 2021. I'm Dr. Beverly Wright, Chief Analytics Strategist at a company called Axis Group and Clinical Professor and Center Director for the Center for Applied Business Analytics at University of South Carolina. Go Gamecocks. I'm so excited to welcome you to the Southern Data Science Conference today and kick off this event. It's presented by Neo4j. Neo4j, I appreciate your commitment to this conference and to data science as a field. So thank you for your sponsorship. This conference is intended to help with your learning, your development, and your networking in data science. What happened was, just to give you a quick history for those of you that are new to Southern Data Science Conference, several years ago, my great colleague, 𝚃𝚘𝚙𝚒𝚌𝚜, shared his vision with me for Southern Data Science Conference. At first I was like, you crazy, that's gonna be a lot of work. But he said, I want a solid conference. I want a great conference with great speakers, with interviews, with networking. I want people to really feel engaged. So that is where he came up with the idea for Southern Data Science Conference, and how forming Southern Data Science Conference would help stimulate data science innovation, encourage collaboration within our field, and really just elevate data science as a practice among practitioners and others. I was immediately on board. Oh, great idea, but it's a lot of work, man. Are you sure you want to do this? And it's such an endeavor, but it's also fairly thankless, by the way. So regardless, Southern Data Science Conference was born. And the conference this year, along with other years, has brought forward fantastic speakers, great networking opportunity, and ways to help you in your journey within data science. By participating in this conference, I really hope that you will have 3 things happen, okay? And I would love to see you guys come up with some goals, even if you just jot them down somewhere. I know it's a Saturday for most people. I guess it might be another day for some people. But I hope that you will accomplish at least one of these 3 things. Number 1, I would love to see you get a renewed sense of excitement and appreciation for data science. That is really my number 1 goal. I hope that that will happen for you, and that this event will energize your interest. Secondly, I hope you'll meet the colleague of your dreams, or maybe 2 or 3. Hey, this is not an exclusive thing, man. It's a conference. You're not getting married or anything. But seriously, whether you are a job seeker, a hiring manager, you're looking for a mentor, or you want to mentor others, or you're looking for a study buddy as part of your master's program in analytics or data science, I hope that you'll meet some great colleagues, because I'm sure that there are several in the chat and there are several speakers that you're going to meet. And then third, lastly, I hope this event will open your eyes for new ways to leverage data science in creative ways. There we go. So thanks again for joining. Now that my opening remarks were not recorded, but that's okay. Mark, I'm going to hand it over to you to go over logistics and the agenda for the meeting.
Once again, thank you very much, Beverly. Appreciate it. Once again, apologies for the recording happening there. So everyone, welcome once again. For today, we have 5 different talks. We end at 12 p.m. Pacific Daylight Time. Then there is right after that, there is a networking event sharply at 12 p.m. or 3 p.m. Eastern Daylight Time. And for those of you who did sign up to do mock interviews, right, we had to sort of pair you with industry mentors. So there was a limited number of slots, limited number of folks that had volunteered, but ultimately we were able to pair about 80-something folks or more. So very grateful for those of you that volunteered to interview and those that volunteered to be interviewed as well. So in terms of the talks that we have today, very, very excited. Lots of stuff to learn. First, we have Andrea. She's going to be up at 9:15 PDT sharp, and she's at Getty Images. And what you're going to learn is about image search. And what's kind of interesting there that I really want everyone to take away is typically we describe things when we search through a textual type format, but images are so rich when it comes to the things that they describe, and essentially describing those things in a human spoken language is maybe not the best way to actually retrieve the images that you want. So we'll learn about how machine learning is actually driving a lot of progress in that domain. Next, we have Andrei. If you have never followed Andrei on LinkedIn, I highly recommend that you do. He shares tons of great papers on machine learning, search, recommendations, and natural language processing. So naturally, he'll be speaking about natural language processing at scale. So he's worked at Apple and Google, and now he's running, he's a VP of engineering, as it says, at Zillow Group. And what's very interesting about their environment is you have both images, you have text, you're doing a lot of things around searching for homes and land. So definitely invite you to think about how you can use the lessons that you learn there in your own production use cases or in your own education. Grid.ai, William Falcon, he is the founder of PyTorch Lightning. For those of you that use PyTorch, you get to see the person that developed it himself. And he launched this company called Grid.ai. Definitely highly recommend that you check it out. And they are focused on making distributed training of machine learning much easier. For those of you that have never really trained models at scale, it's not necessarily a straightforward process. And Grid.ai is definitely making tons of headway into making that a lot easier. So you definitely want to tune in there and take those lessons away. For those of you that do Kaggle, I'm sure Philipp's talk is going to be quite exciting. He is currently world #1 ranked on the leaderboard, and he's going to share basically how can you take the lessons that you learn from Kaggle and apply them to industry. Right? Oftentimes, Kaggle problems are extremely well defined, and those don't always transfer nicely to a real world environment. So once again, you're going to learn a lot there.
Mark, sir.
Yep.
Can you please advance? I think you're talking about people other than Andrei.
Oh, interesting. It's advancing on my side. Gotta love Zoom delays. Give me one sec.
We're still on.
You're still on Andrei?
Yes,
okay.
From Zillow.
Let's do this. Oh, it's always a good time.
We were tracking though.
Yeah, we're going well. It's all right. These are natural things. Let's go. Can you now see Philipp?
Not yet.
Okay. All right. Zoom is not playing nice with me today. Give me one sec. And once again, everyone on the call, really appreciate your patience here with some of the tech difficulties.
At least we didn't have to travel to some conference site.
This is true. So everyone's on their couch relaxing.
That's right. No hotel and all that, away from your family and your dogs.
What about now? Are you able to see it?
It just says Mark M has started screen sharing with a black screen, but we don't see the actual screen.
Good times. Okay, so let's, I'm going to stop sharing, and essentially sort of finish the talk. And our last speaker today is Dr. Alicia Frame. She's from Neo4j. And the thing that I want you to take away from there is there's lots of progress and lots of problems that can be solved with graphs. And this is often a topic that's not taught in school. So you definitely want to be able to digest a lot of that type of material. And there's not many places to learn. So you're learning from the top company doing graph processing and graph data science. So once again, I'll open the floor. And for those of you that are students early in your careers, like Beverly said, please network, follow the speakers on LinkedIn. Don't necessarily connect. That's a lot of connection requests sort of coming in at once. And lastly, I hope that you take all of these lessons from our speakers today and take them to production and take them to accelerate your career. Thank you.
Great. Thanks, Mark. And there is a follow button, by the way. So several of these speakers, if you don't want to connect, or if they're getting too many connection requests, you can always follow somebody, or I think almost always. There's some people that have that restricted as well. But so yes, our first speaker Andrea, are you ready? Great. Andrea, I don't know personally, but I love your background. Andrea comes from a little old company known as Getty Images, and she's been there about 4 years. She's the director of artificial intelligence and machine learning. Looks like you've climbed the ranks at Getty pretty quickly, Andrea. Very impressive. She's also a former teaching assistant at UC Berkeley, another great school, where she taught NLP, quantitative research and methods, and data arts. I just love that. By the way, Andrea, I think it should be called data arts and sciences, not just data sciences. So
Love that.
FYI. And she has other great experience from other small little companies like EY and Apple that you may have heard of. So Andrea, thank you so much for being a part of Southern Data Science 2021. I will let you take it away, ma'am.
Thank you. I'm excited to be here. Just pulling up the screen share, clicking all the right buttons. Seems like you can see it.
You are good to go.
All right. So yeah, I'm really excited to be here today. I'm going to share about image search, specifically how to think about different models and different types of data that may or may not be the most appropriate for different user types within image search. To start off, I'm going to show a video that gives an overview of Getty Images as well as illustrates the power of imagery that will really set up why some of the technical pieces are important. So this should play with sound.
Think about what moves you. A moment, an emotion, a memory, a story, a connection to something real, maybe to something unexpected. We believe in the power of visuals, to ask the questions, to press the issues, to challenge attitudes, to smash through stereotypes. For 25 years, we've collaborated with the world's best photographers, videographers, creative researchers, and the industry's top talent, with unmatched access and unique perspectives. We focus our lens on what's right in the world, what demands attention, and what we aspire to. From the commercial to the eye-opening, revenue generating to society changing, market disrupting to headline driving. From the world's biggest stages to the far reaches of the globe, everything we do is to ensure we have the perfect visual, that it's easy to find, and that it makes a connection. Creative, editorial, archival, custom. Our imagery has the power to move you, and move the world it does.
So hopefully that those visuals did move you in some way. One of the keywords in that video that really strikes me is smashing through stereotypes. And at Getty Images, what we do a lot of to help people find the right image and video is that we show that content in search results. And so trying to making it as easy and intuitive for the customer to find that right image, really leveraging data science, machine learning. And one of, if we are showing in search results stereotypes, we risk perpetuating those and amplifying those out into the world. And so what we really try to do in our search results is smash through those stereotypes and try to break them. And so what do I mean by biases in imagery? These are images from an article that was put out a few years ago by GQ covering the style of climbing. The scene is of these strong men performing some impressive climbing moves. You can see the guy on the top of the rock at the top who's out planking, the guy on the bottom left who is holding his body out horizontally in this really impressive way. And you'll notice that there are some women that are sitting on the rock, sitting in the sun, just sitting back, relaxing. So when this article came out, it was really offensive to Outdoor Research, a climbing company. So what did Outdoor Research do? They went out and they took images to create a parody article where they took the same exact striking images of women doing the same exact impressive moves. You have a woman blinking, woman holding her body out horizontally, while the men sit back just watching. And this is the type of bias that I want to talk about here. Some sort of stereotype in our world. In this case, it's that men climb and women don't, and perpetuating it. And these biases and stereotypes could be anything from gender to race to body shape to income level to age to ability. And when these stereotypes come up in images, they can also show up in image search. So this is an example of our search results for the word nurse. And if you search for the word nurse, you might notice something about these results. And as you might expect, the majority of them that come back are female. And according to the US Census, 88% of US nurses are female. So it's really easy for our photographers to go into a hospital or medical facility and take photos and capture females because that's what's represented. But we see that our search results show 76% female nurses. So this really begs the question, like, should our search results be balanced and inclusive across all genders, or should they show an objective representation? Our customers are asking for more balance and inclusion, and we also really want to smash through those stereotypes. And so what we aim to do is try to balance out the genders that are represented, as well as races, ages, abilities that are reflected in our search results. So for the rest of the talk, I'm going to talk through, this is one of those talks where I'm not going to give answers. I'm only going to give different problems and questions. I'm going to walk through two possible approaches of how to improve this problem. And I'm really going to speak to the different risks and benefits of the data and the types of models. I think as many of you on the Zoom are data practitioners or work with data science in some way, it's so important to think about the technical side as well as some of the social and ethical pieces as well. And so what I'm hoping is that walking through different examples will give just you different things to think about or different ways to ask questions in your own work. All right, so one possible approach. All of our images have keywords on them. These keywords are set out by our photographers. So for example, you have the image of the male in the top left, and you have a keyword in purple that's representing that there's a man in that photo. You have a woman in the bottom left, and you're representing that there's a woman in that photo with those keywords. Those keywords are backed by what we call a model release, a legal document that is signed by any individual person that's in a photo, where they self-identify what their gender, their ethnicity, their age, and they give us permission to use that data. And so these keywords that we have on the images are directly from that model release. We have really high confidence in them because of their strong legal backing. And what you can do with these keywords is you can start to take a probabilistic model and that tries to match a particular distribution. So this is a simplified version here, but what if you were trying to have 50% male of images reflected in your search results? You could have a model that tries to fit that distribution and serve those images up in results. And you could do that across gender, ability, ages, etc. But the key question is, what is that distribution? Should it be 50%? Should it be 70%? How does that differ for different countries and different regions? And that's a decision that maybe you or somebody as a data scientist might make. So some of the risks in this approach is that you're using data that the gender identity data that comes from a model release that comes through a submission platform that has a certain UI and UX that can lead to maybe data being incorrectly input or people forgetting to input data. For example, we've found a bias in our data where people who are white are less likely to indicate white. People that are of a non-white race are more likely to indicate their race. And so you have a skew in the data that is hard to overcome and hard to use. You have the risk of a set percentage of that distribution, and who sets that percentage, who gets control to set that percentage. And then this method also relies on categories. So you have transgender, woman, non-binary gender. Not everyone fits into one of these categories or buckets explicitly. And so you're relying on these different categories, especially if you have them be mutually exclusive. That can be limiting in what you're able to provide in the search results. So what's a completely different approach? One is that we can rely on the image pixels themselves using computer vision. Mark had mentioned that in image search, you often have text-based input and image-based input. And so this is an approach where we're looking at the images only and not considering any sort of language or any sort of words, and seeing what options that gives us. So with computer vision, there's models out there that will detect human faces. So that's what you see in the blue box, is a model is detecting which pixels are attributed to a human face. And with that, it's typically a convolutional neural network. The output of that is an embedding. An embedding you can think of as essentially a vector, often of floating point numbers. And so this embedding or this vector represents the pixels in the image, but not only the pixels, it represents the colors or the skin tones and the patterns and the facial features that are observed when the model looks across many different human faces. And so if you have these embeddings that represent two different faces, you can do a mathematical calculation between them, essentially the distance. That could be a Euclidean distance, a cosine distance, a lot of different types of distances, but essentially you're calculating how close or how far away two different embeddings are or two different faces are. And with these distances, what you can do is you could look across all of your search results and you could detect all of the faces in the searches in the results. And for every pair, you could calculate what that distance is. So here you have the black male in the middle and the black male in the bottom. Their facial features and skin tone are relatively similar to each other. And so you have a smaller distance of 0.3. If you take the black male in the middle and the white woman on the left, you have a much farther distance, that distance of 1.5, because their faces are much more different. And so with these distances, what you can start to do is you can start to say, okay, well, I want a search results that has a wide distribution of these different faces. And so what you're seeing here is for a given search of nurse, there's 2,000 candidate images. Every candidate is given by a blue dot. And you can start to map what is the face distance and then what is the semantic similarity or semantic relevance along the x-axis. And so you could imagine of these 2,000 candidate images, choosing ones that ensure that you have a wide distribution of different face distances. So some of you have probably either seen in the media or seen in your own work some of the concerns with face detection models, that they often create biases. So I'm going to do a deeper look into that model because it's a key part of this approach. And this might be a bit of an overview for some of you that are really familiar with face detection and computer vision. Others, it may be new and help you understand how these biases can come into the model. And I'm going to use a toy example that's based off of dogs instead of faces, just because I think that it's easier to kind of think through the basics in that way. So in our toy example, we have Dan, the data scientist, and he loves dogs. And so he wants to build himself a dog detection model. So to build a dog detection model, he needs a large set of training data. So he goes to his own personal photo library and starts collecting images of his dog, Mowgli, it's golden retriever you see there on the left, and images of not dogs, basically other travels and adventures that are on his photo library. And he could have gone to Google Images to get some images, but those images aren't so great. He could have gone to Getty Images, but those images cost money. So he went to his own photo library. And with this training data in hand, he starts training his model. And the convolutional neural network starts to learn patterns as it sees image of dog after image of dog. And it begins to learn different features. It learns that dogs always have floppy ears. Dogs always have snouts. Sometimes they're open, sometimes they're closed. Dogs always have this golden shaggy hair. So Dan's all excited about his model. It seems to be performing pretty well. And he goes to evaluate it. And what he finds is that it's able to detect his own dog with really high confidence. But other dogs, it's not so good at detecting. Dogs with different shaped ears, dogs with different shaped eyes, dogs with different snouts, dogs with different hair colors or hair textures. And so does this mean that Dan was a doggist in building this model? No, he had no intention of creating a model that discriminated against certain types of dogs. He was purely relying on the training data that was easily available to him, which was in his photo library. And so that's exactly the analogy to face detection is exactly how biases come out in face detection. This is a sample of images that are in some of the training data sets for face detection. And as you'll probably guess, there's a large portion of male and white people in them. Why is that? Because they're often scraped from the web, say in the early 2000s, when there were a lot of white male people online. And when you have these highly biased data sets, what can happen is that the output of the model doesn't function for different groups of people. So here you have a face detection model that's not working for people of color, women, as well as much older and much younger people. And so the reason that this is a problem is if you think back, we were trying to increase the diversity in our search results. And we're using a computer vision model to detect faces that fundamentally has a flaw in it where it can't find the faces of some people. And so that's a big risk where you're trying to improve diversity in the search results, but one of the mechanisms you're using is already cutting out people in the process. Another risk is that the distance measure that I was talking about could potentially be harmful. So if you have someone who identifies as a particular gender, but is their facial features actually look similar to a gender that they don't identify with, the distance will be quite small, but they may be offended by being associated in close distance to that person. You're also really limited to face pixels. So in the first approach, I talked about how you have a gender of who somebody identifies as that is something that they indicate in that legal release. Whereas if you only rely on face pixels or the pixels in an image, you lose any context and someone doesn't have control based off of the pixels. I can't solely identify what gender this person identifies as. So these are two possible approaches. There's many other approaches to try to solve this problem. But what it really comes down to is, do the benefits outweigh the risks? There's no perfect way to improve this problem, but we also know that we for sure do want to improve it. We want to show a balanced and inclusive representation of the world in our search results. And we need some way to do that. And the most likely way is to leverage data and machine learning. But any approach that we have has risks that are involved. And so really breaking down and thinking about what are those risks, the risks in the type of model, the risks of the decisions that are being made by the data scientists, the risks of the coverage of the data that feeds into that model, risks of biases that might exist in the whole system. And how do those risks all stack up and compare to the benefits that might be as a result? Thank you for listening, and thank you to the team that put a lot of thoughtful work into this, as well as many of you that do really thoughtful work in your own practice. There's this work is an evolution. It's not perfect. I welcome any thoughts, questions, concerns, ways we can approach this better or differently. So please don't hesitate to reach out.
Thank you so much.
Yeah, thank you.
We do have one question in the chat, in the Q&A part of the chat. I'm going to read it, and then I'm going to, I think, maybe rephrase it a little bit. But it says, I have a question. How method of image selection you presenting in this lecture can to be good for solution of social problems, and how this method can to help in facing emergency situations such as COVID-19 and natural disasters. So I think what he's asking is, how can the way that we're processing images help in, number one, social good, and number two, in emergency types of real-time situations? I believe that's the question.
Yeah, it's a good question. I think for social purposes, like, absolutely, it can help. I think as I kind of talked about, you really have to weigh the benefits and the risks. For example, face detection is a technology that exists, and it can be used in a lot of different ways. And depending on that use case is really when that technology can be used in maybe a social good way versus a way that's less good. So for example, face detection used for policing purposes, for particular applications, or for detecting criminals might have higher risk associated with it than face detection for unlocking your cell phone. And so the same technology, but it's just used and its application is in very different cases. And so how to really think about what are those applications, and is this the right technology for that application? For natural emergencies like COVID, something that we experienced was that we, like when COVID hit, there were a lot of people that then started wearing masks, but we didn't have either those mask images in our library, and so had to go out and source them from photographers. But then the data that powers our search means that there's a lag to, like if a mask image comes in on day one, it has to collect particular interactions and popularity before it surfaces in the top of search results. And so how do you make a really rapid change to search results to make sure that you have the content available in these natural emergency scenarios so that people can communicate? Like, somebody would probably want to have a picture of a mask if they're doing a campaign about wearing masks and wanting to make sure that content is easy to find.
Fantastic, thank you. And by the way, for those of you interested in data science for good, during closing remarks, we're going to announce the winners of a Data Science for Good hackathon that was conducted recently. The second question, we have 4 altogether, so hopefully we'll get to them. Second question is around inclusion and diversity. To ensure inclusion and diversity, our models need not to be blind toward ethnicity or color by not accounting them at all. We need to correctly identify them first and ensure afterwards that our models are not biased toward any specific group. The question, that's their opinion, and then the question is, would it be legally allowed to identify based on color or ethnicity?
Like in the sense of a face detection model that is saying this person is a particular ethnicity. I'm not exactly sure if that's the exact question. I would say that my opinion is that if you're using pixels alone to detect what someone is, either like what they identify with or what their background is, how their pixels are reflected can be so different than what their true story and what their true background is. So I'm a firm believer that we should not be using pixels alone for cases like that.
Interesting.
Yeah.
Okay. The next question is, how can, if at all, data science be used toward major issues like global peace? Do you see some of this somehow helping us in that area?
What a cool
That's
question.
a huge, I know, it's a huge question.
That's a huge question. While
you think about,
yeah,
you want me to give you a minute on that one?
Well, I'm not going to solve that answer right here, but I do feel like that data science in some cases can cause the opposite, can cause maybe people to like see the world only through their lens and not through the eyes of other people. And so if you can use data science to create a situation like that, then it seems like you must be able to use data science to create the opposite situation. But that's also my optimistic view.
I love it. And I feel like one of the things I just posted about this on LinkedIn actually is that we're lacking empathy for each other. And so maybe some of that is what you're talking about, is a sense of empathy and understanding and perspective for others, which could in turn lead to positive outcomes around global peace.
And I do think, I mean, just one quick follow on to that is that like I said it in the presentation, but I really do believe it, that a lot of us on the call make a lot of decisions when we're building data science models or data pipelines or working with data or deciding what products to build. And a lot of those decisions we make and they don't get seen by a lot of people. And so like, you know, take that responsibility seriously, that you have a lot of influence in how these are built, an opportunity to build them in the right way. And so, you know, take that to heart.
Yeah, absolutely. And then we only have time for one more question. So I'll choose this one that goes swing completely in the other direction toward more technical. There are occasions where there's a lack of representation of different groups or objects. So can you first explain very quickly and simply what are GANs, and are they used in that way to help fill?
Yeah, so GANs are generative adversarial networks is what GANs stand for. And they're essentially a model that is used to generate new images. So what I've talked a lot about here today are images that are taken by a photographer, a human photographer, and then trying to show those images in search. You could imagine a GAN that is used to generate an image from scratch. So essentially from random noise, you're generating an image. I forget the second half of the question.
Oh, it was just, can GANs be used, the generative adversarial networks, toward solving the lack of representation for different groups or objects?
Yeah, it's interesting because GANs in some ways can generate things that are unseen by seeing similar patterns across many different areas and generating them. They can also be very limited because they can't imagine something completely new or completely unseen. And so GANs still have a lot of bias. The ones that exist today that are trained on openly available data sets still have skews and biases in them because they're trained on, say, celebrity data sets that are skewed towards different groups of people or a particular look. And so in some sense, GANs you would think would have the potential, but I think that they're still really dependent on having the initial training data. So I don't think that they're going to solve this problem completely, no. Beverly, you're on mute. Sorry.
Thank you. Yes, thank you so much for your time with us today, for your wonderful talk. And Getty Images is very lucky to have you. So big round of applause for you.
Definitely.
And Mark, I'll hand it over to you.
Yeah, actually, Andrea, don't leave yet. We're gonna keep you on a little Q&A. We're waiting for Andrei to join the session, so we get to have hopefully you on a little longer as we sort of wait for him to come online to do NLP at scale.
Oh, that's great. That's great, because we had a lot of questions for you that weren't answered. And I was going to ask if you had time, if you could hang out a little bit, you could see some of these questions that are coming in as a panelist. And so if we don't get to all of them, then hopefully you can answer them in the Q&A. So since we have another minute, let's see, who do we like here? Okay, yes, I like this one. There's another question that is, we talk about underrepresented, but let's see, underrepresented, would it help to show more images of the minority, like disproportionately more than there are in a given group? Like, is that, I think the question is around, is it beneficial to swing deliberately in the wrong direction or in another direction because you see what I mean?
Yeah, it's a really good question. And that's, I mean, do you deliberately swing to one extreme? Do you have a pure balance? Do you show objectively what exists in the world? And something that's really interesting, at least in the Getty Images search case, is like, we want to reflect this, the balance and inclusive representation. We also want to make it easy for people to find the images that they need to. So if you imagine someone in a particular neighborhood or community where they need to find a white female, and if we make that really hard, then they're not going to be able to find the content that they need either. And so I think that it's important to have it be really balanced and inclusive, as opposed to swinging really far one direction or the other.
Got it. Nice. Okay.
So Andrei is
Yes.
on. I think we may have had a little bit of technical difficulty, and I promoted him to a panelist. So if he can confirm, there he is.
Thank you again.
Thank you very much.
Thank you, Andrea. Appreciate it.
Bye.
Hi, should I start?
Sure. Oh, give me one sec. Beverly, did you wanted to cue in Dr. Lopatenko?
We can go ahead and start him since he's a couple minutes behind.
Cool. All right.
Just make sure you give us a little background, if you don't mind, please.
So I can start, right? Sorry, we had some.
No worries. You're good.
Yep, go.
You can start.
Okay, let me share my screen. Yeah, I apologize. Yeah, I had some problems connecting share presentation.
No worries. No worries. And we can see your screen just fine. Thank you.
Yeah. Hello, my name is Andrea Lopatenko. I will talk a little bit more about myself later to introduce, but so my presentation is about natural language at scale, natural language processing at scale, how to apply, how to build NLP systems for your business. What's the focus of this talk? I will talk more about how to implement and use natural language processing in your organization at scale for large business impact with low development infrastructure cost. How to build an NLP system solving many different business problems and improving customer experience. The focus of this talk is more about NLP systems, right? If you go to academic papers, typically they talk about beta models. Like there is a lot of talking about like database approach to machine learning pioneered by Andrea and G. But I will focus more on building NLP systems, how to build systems fast, reliably, how to prove value of NLP, and then beta models and beta data come as a second step after building the systems. When I talk NLP at scale, what do I mean at scale? So there are like multiple dimensions. The most important in many business applications are so building NLP systems which can easily serve very different business tasks, right? Not just focused on some particular dialogue chatbot experience or something else, but system which can easily scale horizontally and serve many different business tasks. Like some will be document classification for legal, some will be query classification and query understanding for your online search. It will be a dialogue system for customer support. So how to build NLP systems which are scalable by many different business tasks. And another, of course, very important scalability is high loads, right? Because we will have huge number of documents to be processed per second, number of documents to be processed in one batch. number of queries per second, which can go for some systems to millions in second and so on. So this is another important dimension of scalability. So, and again, I will focus on systems aspect of building NLP systems, how to build end-to-end systems, train, deploy, integrate with business, and then learning like better models come after that. Why I'm talking about this? I have experience with NLP since 2006, so it will be 15 years. I started in early Google. I was co-contributor to Google Search when we just started to be better than Yahoo. And I contributed multiple different components of Google Search, and many of them NLP based. I was co-founder of Apple Map Search. We built Apple Map Search, contributed Walmart Search, led Walmart team, eBay Search, science teams, engineering team. I was like currently in Zillow, leading NLP, conversational AI search. I worked contributed to startups. Oslo, which I was co-founder, was acquired by Facebook in 2017. It's conversational AI startup, NLP based, and so on, right? So NLP is a key technology for many different business needs. And in 2021, now I want to argue it's quite relatively easy to build and very rapidly build high quality NLP systems than it was several years ago. And I want to share my experience with that so that people can. So mathematic examples, why NLP is good, right? Because if you go to popular media, to tech media, there are like very narrow focus on chatbots. Actually, NLP is super useful, well beyond, and majority of its value is coming from other like customer-facing online systems, search systems. Would it be Google, Apple, Amazon, Zillow, all online search, right? Understanding of queries is NLP. Understanding of documents, extracting right information from documents, understanding what this document about is NLP. And there are a lot of new improvements because of BERT transformers, but actually all the systems based on NLP for a very long time. Most of them, like just as you build them, they have substantial amount of NLP inside. Multi-billion impact on the industry. NLP is key in search. A customer-facing online system like recommendations where NLP is not obvious, right? It seems you click on item, what are related items. How you decide that? Many properties of items you can use as a like embedding techniques, so representing through structured information extracted by NLP techniques. So recommendation systems are largely driven by NLP also, as NLP is one of key feature providers for recommendation engines. Other use case, question answering system, facing, so those two systems I described before, mostly customer facing, facing business. You have huge amount of information in your company, other unstructured information, like unstructured source, like the databases, or unstructured, like just big amounts of text. And you build a smart analytics which can answer natural language questions, or like good example, a Bloomberg trade order management system, right? Or like just a frequently asked question system which can find proper paragraph. NLP is super useful tool to create this sort of systems, and they've proven already big value for businesses. Analysis of conversation. So still majority of businesses use conversation you call like as a sales agent or customer support agents, or other you call your bank for financial support. And you know, like there are some work to replace humans, but does not work very well. But still, even human-to-human interaction, you can transcribe and use NLP to understand well the needs of this customer were addressed. How well performs this particular agent? What makes better performing agents performing better than not so performing agent, right? So using this huge amount of information, using NLP techniques, you can understand a lot about customers, about your business, about how to improve your business. There are like last year, several startups in this area passed unicorn just because they're doing solutions based on NLP for this area. Huge impact, big impact. And there are multiple different, not only NLP voice analysis to understand like for emergency services about state of the person and so on. Case 5, dialogue systems, chatbots, like Zillow very recently launched Zillow Rental Manager bot with very big success, proven a really big improvement of our services to our customers. Amazon customer support, which perhaps more people know, right, just because they have more customers. Like how to provide support for your customer to know state of the order, state of the item, and so on, right? Proven to have a big value. There are like book which there are several articles which shows how much monetary value, but another is big value, customer facing and business facing dialogue systems. Another mathematic example, like every system which like Zillow imports a lot of listings. Amazon, Walmart also imports a lot of data about e-commerce products. Understanding this is extracting structured information, is also NLP. Typical NLP application works since like Amazon started, since other companies started. So everybody does this structured understanding of unstructured information with huge value for the business, driving really business in majority of cases. So summary of this is like, if you go to tech media, typically they talk about NLP, dialogue system, actually much huge multi-billion value in industries coming from many other applications. And those applications are very different in their nature. They're very different from NLP point of view, classification, extraction, summarization, like dialogues, next state prediction, very different applications from NLP point of view, but very different also like technical applications from how they implemented and different business impact. So how to build systems to do all this stuff, right? As again emphasized, like chatbots is just small part. Don't think about when they talk about NLP. Don't think about them. There are many other big applications. A typical NLP serving scenarios. There are multiple different kind of typical high-level online serving, right? When you have to serve big number of models, like for example, for search engine, people come to your search engine, they type a request and you want to understand what this query about. Typically, like as it scales, it becomes complicated. You may have hundreds of models there, very strong requirements for performance, right? You may have like 50 milliseconds to run all these 100 models. Not more per one query. You may have 100,000 queries per second, depending on systems. Some systems like Google may have million, right? So online serving, performance critical, very special scenario, one of cases of NLP serving. Other cases, streaming. You have set of documents coming to you, like for example, you crawl web, or you have items, descriptions from listings you buy, or other like coming like continuously. And you want to extract information, classify them, and do all other NLP stuff. Typically, latency through output requirements are more relaxed than online serving, but still you have quite strong. You may have billions of documents per day or hundreds of millions, depending on your business. Latency limits, typically you don't need like 50 milliseconds in this scenarios, it may be longer, but it's still some reasonable, right? Some maybe minute, 10 seconds, 1 hour, depending on your case. And then you have batch scenarios when you have large collections of documents you already have, you want to process all of them in one large chunk. And you do this periodically by different, because as a model update or information update. And so those kind of three big cases, and actually there are more, but those big three cases for which you build NLP systems. So what about NLP, right? If you read articles which are published by academia, right, it's mostly about, yes, we build this new model, we train this new way, like look at our metrics, like it's like 5% better than previous models, SAT, like state-of-the-art model. NLP systems in the industry is not just model, it's serving model in production under various serving environments, right? With very different requirements. Some of them online serving, some of them streaming, some of them other ways. Very different, can be hardware requirements and so on. Training models to your business, not just some like academic metrics. Collecting and annotating data to train models, validate models, understand models. Deploying models from research to production such that it will be very easy for researchers, right? You expect if scientists works and they create a new model, you don't expect them to go and understand how our CI/CD works. They just deploy models, just put into, let's say, GitLab, and this model pick up, deployed, validated, and performs there, right? How to create environments such that hundreds of scientists can work and deliver for your NLP in parallel. Testing model, validating model, monitoring models for different parameters, like physical performance, accuracy, compliance, fairness, model performance, end-to-end system performance is most important. Integrating models with streams of production data and integrating with outstreams, right? It can be a part of search engine, deliver results. It may be about like extracting data about your customer and delivering this to Salesforce or anything else, so integrating them with multiple your business systems. Again, majority, like what I want to argue, like system development is really important. Majority of gains from business point of view you get not just because you implement some recent model which is like 5% better than previous model, but from better engineering, high performance, reliable, robust, scalable systems which are integrated with multiple business and customer applications, monitorable, debuggable. You can imagine, assuming business has like 5 different lines of business or 10s, right? If you improve, like you build an NLP for one of them, if you improve 5%, in the best case, you will improve 5% revenue. If you create and deploy your NLP system and deploy across 10 different lines of business, you will have much bigger revenue gain. So for successful NLP projects, the focus should be on reliability, robustness, performance, operational excellence, development, engineering quality, science quality, openness for collaboration. Once systems works and brings value, then you can focus on bringing state-of-the-art model, improving these changes here and there. So like kind of big blocks, typically what you build, right? One is scientist workbench. So this is about finding the best models, right? How to find the best model for this particular needs. And for this, you need annotation tools, data and processing and data management tools, of course, integrated with your production environment. Like you want to have data which are in production, data which really important for you to be in scientist environment, important big task, right? More improving model training, how to make such that models train like in parallel, very rapidly, tuning, model management, how to like this experimentation management, all this stuff. So I would say a scientist workbench, how to create the best models. Deployment tools, given models delivered by scientists and not just models, data, storing them like other values, how to create very robust, very fast, very efficient deployment of these models into various production environments. And of course, validation on the way. Inference, right? It's also very important. How to serve your model in the best way. How to serve them with minimum hardware cost or like cloud cost. How to serve them with the best latency and through output requirements, such as they serve their business or customer in the best way. How to validate them online. How to measure if something going wrong with model, detect it very fast and roll back or do some other correcting actions, right? So inference, and again, integration within streams and outstreams of data and business systems. So this kind of big blocks, very high level for building NLP systems. So there are, I would argue, like, again, it's flexible, but there are three kind of big ways, big high level types you can build an NLP system. One is cloud native. So you take some components from cloud, build your system based on them. From scratch, you can build by your own from scratch, right? C++, Java, Python. Or you can use hybrid approach between these two. Some blocks you use cloud, some you use on your own. Cloud native, right? Multiple ways to build cloud-based NLP systems. So I'm talking about Amazon mostly here, just because I know Amazon, I know Google Cloud has a lot of other components, other providers have others. I don't talk about them because I just don't know them deeply. I'm talking mostly Amazon, right? There is big number of very different levels. So like Amazon Comprehend, kind of they're trying to make NLP after ML, right? Which works for some cases does not work, but for some cases works. You can use at that level. You can go to more low level, use SageMaker and then build on top of it, right? So there are multiple different. You want to convert speech to text, you can use like either build your own or use actually service from Amazon, and there are many other. So what are pros? It's very fast to develop a prototype and make a working systems. Low development cost, easy to integrate with other systems on the same cloud, hard to integrate on other clouds. Like cheap operations for managed solutions, right? You can develop like if you need a Kubeflow, like let's say Kubeflow, and you can use managed solution, right? Just for example, it's much easier than to create your own operations for that. Cons, high cloud and compute costs. Of course, you pay for the stuff. Low flexibility in type of models to develop types of framework supporting by those systems. And then if you want to improve, like have really state-of-the-art model, it's not necessarily supported by them. You have to find way to work around. Performance is not maximally optimized for hardware requirements. Depends, right? So doing good work, but if you need some extreme performance, not that good. Integration with non-cloud system requires substantial efforts. Again, very good to develop MLOps if you use those cloud solutions. Like for example, Amazon have huge number like code pipeline, code build, HR container registry, for serving AWS batch for batch serving. There are different other things. So if you want to build MLOps using all this stuff, quite easy, quite fast. Easily to adopt if you have cloud, your cloud production environment based on the same cloud, very easy to adopt your NLP in the same, your stuff, your other stuff. Easy to build multi-environments deployment scenarios. It's for cloud native. Build from scratch, right? This is how we typically would do any of this NLP task 10 years ago. And now you have like other options, like there is huge amount of open source, right? So like build from scratch, not necessarily building everything from zero. You can use, of course, a lot of open source available, huge amount, a lot of them super useful, frequently requires some improvement, but there is a lot of PyTorch serving for low levels, PyTorch and PyTorch serving for low level training and serving TensorFlow also. Hugging fast transformers, so large collections of pre-trained models for NLP, NLP environment. They have very good evaluation. I don't use like their models, but like for evaluations, they have really good framework to build your evaluation. Spacer, Docano for notations, so big amount of very different like blocks you can use to build your system, right? More opportunities for optimization of accuracy models and performance of systems, customization to your customer needs, owning the software is big block. Cons, of course, it requires longer prototyping, production, development times, high operational costs if you're doing it on your own. In some cases, it's the only way, right? So you might have, like, again, like I said, described million of queries per second, and you have very high hardware cost, right? You have to optimize to particular types of hardware. You can get a lot of from flash drive storage and so on, right? Typically, cloud solutions are not good for that. So in some cases, it's really important. It's the only way to build your own system is to build your own, which will be super optimized. So like, but it's not always, not for every businesses, for some particular set of businesses, right? And then you build mix of cloud and custom build, right? So you can do some block from cloud providers, some block on your own. There are different ways. You can do as a horizontal, let's say you use for inference, you use what Amazon infrastructure, but for data scientists, applied science lab, everything training, you create your own. On vertical, you can use low-level components of cloud, high level of your own. There are different ways, right? There are multiple cloud solutions for serving, as an example. So this solution has kind of in between previous two, relatively rapid development and deployment, relatively smaller, more expensive serving and so on. So it's between previous two. There are multiple ways how you can do this hybrid solutions, right? Mix of cloud and custom build. Frequently requires like most of cloud solutions, right? Let's say you use Kubeflow based on Amazon or Google. And you know, like they say they support, let's say they have operator for this particular serving framework. Actually, then you start working for this, it's not so good, right? You have to improve this, you have to go inside open source and implement this. So don't expect that like these cloud components you will use will be addressing 100% of your needs. Frequently you will need to optimize, improve them, solve their bugs, create your own version and so on. Many tools are available, right, at different levels. Kubeflow, Cortex, Hydrosphere, like Seldon, Neptune, MLflow, many different for different components. What you build, like again, NLP system is very big at the end. From training, from lab environment to production environment to MLOps environment, huge number of components. And you can use, there are a lot of open source or cloud solutions for some of them. So you can build this kind of mixed Lego system. Part is yours, part is based on solutions. Again, there are like good solutions, like I would say reusable, like for serving, you have Kubeflow pipelines and to-end orchestration, right? Again, it will not serve your online scenarios, it will serve serving scenarios, streaming scenarios, Seldon, TF serving, streaming. For applied scientists workbench, there are a lot of also very good open source solutions, like of course Jupyter and like derivatives, Catlibs, ModelDB, model analysis, if you're based on TensorFlow, TensorFlow Transform for data transformation, so on. So there are a lot of components to create applied scientists workbench, right? And of course, there are low levels as big frameworks to serve. Like adopting and building an NLP system for business, right? So like everybody knows about NLP now, right? Everybody's like, it was like search engines 10 years ago, right? Everybody's excited. Business, I'm talking about businesses, right? Business part, not just technical part of your organization. But there are a lot of uncertainties. Will it really bring money or not? So to make it successfully, you have to iterate very fast. You have to implement system very rapidly. It's very important that you can prove value of business. We invest, let's say, 5 people for half of a year, and we'll create 50 million value. Okay, works well. Let's invest now more, and we will get billion dollar value, right? But you have to iterate very fast with low costs to prove value and then come back and build bigger systems, bigger impact, right? And as also, like as you work for business priorities change very rapidly. So your tech organization must be capable to adopt very fast change of business priorities. So velocity is key requirement, right? That's why I argue a little bit into cloud solution as first and then building your own. So systems must follow this velocity requirement. And one of solutions is not to commit to one of those ways how you build NLP systems, but like if you build new NLP stack for the company, build something fast and rapid, prove the value, cloud solution usually good for that. But then once value is proven, you have more resources, more people, you can move to more cost optimized, performance optimized, accuracy optimized solutions. So not necessarily, so it's important also to build system which will be available. I will talk about this a little later. Trade-offs, right? Everybody talks about deep neural transformer-based proved huge value. Everybody use them, right? But it's not necessary to use only them, right? Sometimes you can get 10% model accuracy improvement, but we lose 10 to 90% lose in latency. What is important for your business? Sometimes actually this 90% of change in latency can mean more than 10% of model accuracy, because you have to process like 10 billion documents per day, and for this you need to spend many more nodes. It will cost you like huge amount of money, right? So very important to have inside your system this flexibility to use very different type of modeling, to adopt very different latency, so output, accuracy requirements, and system design must support all this stuff, must different trade-offs choices, but also organizational structure and analytics ROI assessment must be capable to understand this and must support making such decisions, and org structure must support such decisions. System availability should be a part of design as you build this, because if you build system, it's not available, it will cost you huge costs in future. There are very important dimensions like to be taken as you build system from scratch at the very first steps. Number of human languages, domain area languages should be adoptable, should be available, should be scalable. Loads, like you build system for 1 QPS requirements, and you have in 2 years like 10 times more. And it's the number of messages, amount of information. System should be easily scalable, cheaply, to much higher requirements than you built it at the beginning. Number of different models, a number of different types of models, right? You build for 5 models, and then in a few years you have hundreds of different NLP models serving very different needs, businesses and needs, customer needs. A number of developers and scientists working simultaneously, like good design of the system should support this, right? Such that you will have 10 times more people in 1 year than you have now. Number of metric systems monitored and models are monitored. The amounts of data and training and serving. Number of use cases, number of deployments, right? You all might have systems like built now for 1 data center, but then you need to serve it in multiple different and so on, right? So scalability and availability is very important part of the design of the system if you care about long-term success of your system. Applied scientist workbench, right? Serving scenarios are typically very different for different business use cases, different customer needs, but applied science is more shareable, right? And once you build one applied scientist workbench such that scientists can share their models between each other, can share their training data, validation data, can share their metrics, is huge benefit for your end-to-end operations. So I would argue as you build NLP systems, you may have very different serving scenarios, like serving systems as part of the systems. But it pays you back if you create one applied scientist workbench to share, monitor, train, deploy models, to share training data and so on. So and actually there is very little done in open source. If you go to open source community, everything for inference, very few good solutions for applied scientist workbench. MLOps very important, right? As you deploy models in productions, support the frequent deployment of models. As models are improved, you will have like multiple models per week, or continuously deploying new. So as integration of NLP scientist workbench with production, environment validation of model scalability. You like how like if you have like sometimes peak of traffic, which is maybe 2 orders of magnitude higher than normal traffic, will your environment scale by NLP to this big amount of traffic, right, of incoming data? So creating proper ML ops is crucial for success of NLP systems. Very important, like to validate model for performance, both model and end-to-end impact on the system, like customer conversion, global data changes, incoming data quality issues, system performance, uptime, biases, compliances, fairness, significant changes, and build infrastructure to support all of this. NLP libraries, huge set of libraries available now from all traditional NLP, like SRF Suite, Stanford Core NLP, and so on, to new technologies, right? We have Hugging Face Transformers, this kind of superstar, Alien NLP, PyTorch NLP, Flay NLP, Detects from LinkedIn, many other deep learning-based NLP libraries. Each of them has advantages, disadvantages. So don't commit that you'll be using only one, and you build a lot on top of it to go inside of them. So there is a lot of open source. Good. Don't hesitate to get inside open source. Like one of my projects, we use Stanford Library Performance, improved 10x performance, just implementing multi-threading than it has. So you can do a lot of big advantages for your organization going inside open source. There are more high-level like NLP libraries, like building like dialogue systems like Rasa, then you have NVIDIA Jarvis for like NVIDIA Nemo if you need to build automated speech recognition, which is not NLP, but actually part of many pre-NLP systems, how you get your data, right? Parallel AI from Facebook to build dialogue systems. Neural, of course, one of NLP applications is machine translation to build neural machine translations. Spark NLP like has a lot of like models as very useful in healthcare domain.
Dr. Ellen, we're about to run out of time. If
yeah,
you
1 minute.
Give us
one
minute.
Yeah, okay. Yeah, so like very important to share again, as I said, training data sets. Then a very important metrics development for NLP systems, right? And want to emphasize it's super important to measure, not to just drive NLP metrics, but end-to-end system performance, how a system affects your final business. So let's like be faster. A continuous improvement, so never expect that NLP system will be one step. It will be a continuous process, how to improve it, so it requires understanding what's going wrong, what's going correct now, and how to improve this. So it will be always continuous process. And let me go fast. So basically, conclusion, right? Building NLP systems is a relatively easy task now due to abundance of open source cloud solutions. Experience share it, right? But don't it's a relatively easy task. You can build very big impact NLP systems with low initial investment costs. But nevertheless, like once you start to scale system for high load, low computing costs, it will be substantial amount of work to do to make the system really bringing big impact on business. And so, yeah, thank you very much.
All right, everyone, welcome back. Getting a little ready. Hopefully you got your coffee, water, took a little break. And up next, we have William Falcon from Grid.ai. So he's the creator of PyTorch Lightning. And he recently, like I said, founded Grid.ai. So super excited that he's out here. And I think one of the key things that I want you to focus on is, PyTorch Lightning is focused on research and production as well. But also, he's been able to take this thing and basically scale it to production. So in addition to that, he created PyTorch Lightning while doing his PhD at NYU, and he was a PhD researcher at Facebook.ai. And basically, Lightning allows users to scale models without the boilerplate, and Grid essentially allows you to do large scale training on the cloud. So I'll let William take it over. Thanks for joining us.
Yes, thank you for having me. And this is going to be interactive, obviously, so I hope people ask questions and everything else. So let me just share my screen so you guys can see this guy. All right, can we see this?
Yep. Well,
Okay.
hang on. It looks like it's a black screen right now. It didn't quite come up. There we go. Now we see it.
All right, perfect. Yeah, so again, very excited to be here. I'm William Falcon. I'm the creator of PyTorch Lightning and the co-founder of Grid.ai. I guess I'd love to know who has not heard of PyTorch Lightning. Just comment, I guess. And I guess if you have heard of it and haven't tried it, go ahead and just put a +1 or a hand or something there as well. But yeah, so Lightning really came from trying to train models at scale. It's just something I've been working on for many years at this point. It was probably 2017, 16, the first kind of like internal lines of code I wrote for that. And then it wasn't really open source until 2019 because, I was doing a lot of research at the time. So I didn't really have time to like make it open sourceable, and things changed a lot. So when I started my PhD, I started working on NLP. I had come from a startup. I had a startup that was doing NLP at scale, and we were helping low-income students figure out how to pay for college. And we were using, this was pre-transformers. We were using like 𝚃𝚘𝚒𝚒𝚑 and all these other models, and so there were a lot of really good learnings there. And so when I started my PhD, I started working on NLP research, and so the first versions of Lightning were focused on that. And then we moved into audio and speech, syntheses, that kind of stuff. And then after that into video and images. And then while I was at Facebook AI Research, we mostly focus on large scale self-supervised learning. So that's really where Lightning got a lot of its scaling up abilities, I guess, and obviously worked very closely with the internal people at PyTorch. You know, I saw here Parlay and a few other teams. They're very good friends, and really helped kind of, you know, put a lot of things into Lightning that we see today. And Lightning today is driven by community. We have over 500 contributors worldwide, mostly PhDs, mostly focused on AI. These are, you know, people at big labs like Facebook, people at universities, you know, the largest, most important AI labs in the world as well. So as soon as a new thing comes out, you know, anything that's kind of state of the art or cutting edge, a new technique, you know, a new way of doing distributed training, a new way of, I don't know, like stochastic rate averaging or gradient checkpointing, or all these little tricks, we immediately code them up. It's, you know, it doesn't even take a week for us to do that. And then they're also available to everyone in the world through Lightning. So you don't have to be an expert. You just use Lightning and you turn it on. You just say, hey, I want to do, you know, I don't know, stochastic rate averaging, and then it just works. So you get really, basically you have the access to us, right? The people who are building a lot of the stuff, the researchers. And you know, the same people through Grid, we're basically helping scale that up, right? So we've all been in production settings as well. And training at scale is really hard, right? And iteration speed is really what makes a big difference. So that's a high level, but I'm gonna go through and kind of, you know, talk about both. So, you know, go to the PyTorch lightning.ai and you'll see the kind of landing page there. And then you can click on that star area, and then that'll take you to the GitHub repo where you can see sample code and everything else. And then, you know, obviously love any GitHub stars you guys want to throw our way. And in Lightning, like I said, it's been, I think we're past 3 million downloads at this point. Lightning is being used in over, I don't know, 3,000-4,000 companies across the world now. And, you know, probably a lot of the systems you guys touched today in, you know, major social media apps, that kind of stuff, somehow touches Lightning code at some point in its life. So that's pretty cool. So this is very, very well tested at scale. You know, at like Facebook scale, for example, we partner really closely with them. So, you know, if you're ever wondering like, hey, is this code going to work really well? Is it going to work for my use cases? Pretty confident it will. So now, you know, Grid, to go to Grid, you can go to this link here. So platform.grid.ai. And, you know, if you guys want to follow along, go ahead. We're just going to do a quick demo. So basically, go to platform.grid.ai. And then there, you know, choose a way to log in, right? So you're going to be able to log in with Google or GitHub. And what we're going to do right now is we're going to basically, you know, take a GitHub repo, one of your GitHub repos or one of the public ones that we have. It doesn't matter what it is, right? As long as it's Python, and you can, we're going to run it, right? So preferably it's a machine learning model, obviously. So go ahead and log in. You're going to have to do some sort of authentication with phones. So I'll wait a few minutes for people to get there. So again, platform.grid.ai. And then go ahead and log in. And let me know, well, this is where you should land. I mean, your page will be empty, but it'll be here. And you'll have $25 in free credits as well. So, okay. So now if you don't have code ready, you can obviously click that hello CFAR10 example, and that will run code. Now, what I'm showing you here is on the UI. You can do exactly the same stuff through the CLI. It's just a lot easier to kind of run these things through the UI. So on the top right, you're going to have, oh, sorry, this slide is off. Okay. So if you don't have a repo, we have this one. This is, I just picked one. This is from the PyTorch examples, and this is a DC GAN. Again, I just want to show you, this works for, you know, complicated code, complicated repos, complicated project structures, single files, you know, whatever you want. In this case, this is not modified. We're not touching the code, right? So the beauty about Grid is that you don't have to actually change anything about your code to run at scale. You just plug it in and go. You know, obviously, if your requirements and different things start getting a little bit hairy, we can also let you run your own Docker images and stuff like that. So go to this link here. And if you don't have, you know, something that you want to run, it should be an executable, like a main.py, where you have some sort of training code that will start going. So, you know, if you're using Lightning, for example, it'll be where you'd call .fit, right? So you load data, you load the model, and then you start training. So whatever that file is, find that and just copy that link from GitHub. And then on Grid, go to new run, and a run is going to be a hyperparameter sweep, basically. You know, if you don't want to sweep, you just run one file and it's fine. But this is going to basically run it asynchronously. There's another thing called a session where it's basically kind of like a collab, except that you also have access to your data at scale. So if you have like 30, 100 terabytes of data, you can access it there interactively. And you can also use as many GPUs as you want, right? So you can spin up a machine with 2 8 GPUs and so on. So we're going to do a run though. So if you click on the run, you just paste that link, that file up there, press enter, and then you'll see it kind of populate. And then you won't be able to use GPUs unless you validate, sorry, your credit card. So you'll be able to use CPUs for right now. And then, and you don't have a data store, but if you were to have one, for example, it would be here. So in this case, I've uploaded ImageNet, and so I could attach ImageNet to my job so that the model basically starts training. This is really powerful because, you know, beyond like very simple academic use cases, most of your data sets are going to be ginormous, and the bottleneck most of the time is going to be how you load the data into the models, right? So, you know, whatever code you're using, Grid will make sure that the data will never be the bottleneck, because the way we optimize, how, you know, the disks that we're using, how we pull the data, caching, all this other stuff under the hood. And we obviously, you know, do this a lot, and this is kind of like our bread and butter. So we'll have a lot of the best practices embedded in there as well. And then, you know, if you're using Lightning, then basically you don't have to worry about any bottlenecks. We've already scaled that up. We have a lot of tests that measure speed and performance. And if you're using other frameworks, then it's kind of on you to make sure that you don't have bottlenecks in your code. So here I would attach ImageNet. I'm not going to do that here. And then, sorry, I guess a slide. Okay, great. Yeah, so once you attach the data store, which we don't have one right now, you can enable spot instances, right? And then select the machine that you want. So again, you won't be able to run on GPUs unless you validate, but spot instances are basically going to let you pay like ridiculously cheap prices for this stuff, and Grid will automatically just make it run. And the caveat though is that you know, Amazon can kill your machine, and then you know your code is kind of dead. But Grid automatically stores your artifacts. Anything that comes out of the model gets stored, so you won't actually lose anything. And you can always restart that job by passing in like a checkpoint or a file for the model to load, and then off you go. And then if you use Lightning, this will be automated basically in the next few weeks. So you don't have to do anything, just enable a spot and then it'll just train. So you can train basically for many weeks and months without doing anything, and it will be extremely cheap. So here, you know, you can choose 2 CPUs, very cheap instance. Spot is probably like a cent, I assume. And then that's basically it. So at this point, you can just kind of run that code, right? You can, at the bottom, there's a button where you would say, oops, sorry. Yeah, at the bottom here on the right, there's a kind of start button. Now, if your script takes arguments like flags, you can put them in here, right? So dash dash whatever or dash whatever, and then and just go ahead and treat it like a command line. Just type in whatever you want, the arguments, and then it'll go. Obviously, when you're running, for example, on GPU, so this example is using the GAN that PyTorch has. So this model can run on CPUs. In this case, if I wanted to use GPUs, which I'm showing in the demo here, but you'll be using CPUs, that particular script has 2 flags, one called CUDA and one called NGPU2. And so if you paste those 2 in, you select 2 GPUs on this dropdown and you hit go, then the model is going to train across 2 GPUs automatically without you having to do anything. With Lightning, this is already plugged in. You can say, we have multi-node as well today. So basically you can run a model, and it doesn't have to be Lightning, it can be anything, but when you use it with Lightning, you can basically say, okay, I want 128 GPUs, and you hit start, and we will actually spin up, you know, the 32 machines with 8 GPUs and like orchestrate everything automatically, and then things would just start going. So you don't have to deal with anything, and like forget about MLOps, right? Like that doesn't really exist here. Yeah, you're just training models. And then, you know, the job will start. You'll see this depending on cloud availability. It could take a few seconds to a few minutes, depending how many users on the platform and so on. This is running on the public cloud, right? So obviously your enterprise data and different things like that, you wouldn't be using this. We have teams and enterprise tiers where you can actually do that, and we'll actually deploy it on your own VPC and on-prem and whatever you want. So we'll orchestrate things for you on your behalf on your whatever cloud you're using. Any questions there before I continue?
I think some of the questions are a little broader in nature, not directly related to what you just covered. So if you want to go forward, feel free to do so.
Okay, perfect. Great. All right. So there, like I said, there's a CLI version of this. So if you want to do this in the CLI, you can do this today, right? So go on your laptop, type in pip install lightning grid, then that's going to install the package, right? So I'll give you guys a second to do that. And then you can just say grid login, and then that's going to open up the UI and then show you what your API keys and everything are. Then you just go ahead and paste those and then press enter. Here, I would clone a GitHub repo. Maybe you already have one on your computer, right? So again, I just cloned this. And then I'm going to move to the folder where the script is. You don't have to do that, but I think it's easier for me. So, and then I just go, if I wanted to run that file on my local machine, I would say python main.py, right? And that would start running on my local laptop. So let's pause there. And then let's take that idea of python main.py, right? So this is kind of how you would do things locally, right? Or even if you SSH into a machine and then you do it there, you just hit things. So if you want to run in the cloud with Grid, all you have to do is replace this word Python with grid run. That's it, right? So this is going to do exactly the same thing now, except it's going to be in the cloud. So you don't have to do anything. This is going to obviously run on a CPU machine because I haven't specified anything special about it. So if I wanted to pass in some flags, right, to the script, I can do that. I just pass in the flags at the end. In this case, I'm saying, hey, I want to run on 2 GPUs. So then I'm going to have to also tell Grid, hey, I need a machine with 2 GPUs, right? So then I'll say, hey, I want an instance type with 2 V100s with 16 gigs each. And then you basically say, okay, and of that, I want to use 2 GPUs. And the reason this is here is because I could actually run 2 models on the same machine, each one using 1 GPU with Grid. If I just say GPUs equals 1, and then I pass in, and then I call this thing twice, right? So it's going to use the same machine. So in this case, I'm saying, no, just use both GPUs. Again, at scale, I can basically just do this, right? So I can say multi-node, for example. I would just say, hey, I want 32 GPUs and I want to use this one machine. And then Grid is just going to figure it out and scale it up, right? With Lightning, this is like very trivial. You can use TensorFlow and Keras and everything else, but then you would have to configure all the distributed stuff under the hood, which is extremely non-trivial to do. So now we're going to kind of go into Lightning. So I want to talk about, we have a few libraries within the Lightning ecosystem. We have Flash, which is really meant for baselines. And these baselines are like task driven, right? So you want to do text classification, video classification, object detection, whatever you want. You're able to basically load a checkpoint if you want, and then just predict, right? So you can say, hey, predict on these sentences, and then you get the predictions live. You can also train, right? So it's very easy, but this is meant to get you can literally do like state-of-the-art NLP and computer vision within a few minutes by using this, right? And this is a lot of the work that we put in. This is integrated with all the hubs, right? So any of the model hubs out there, they all work, right? So you can use Hugging Face models that are here as well. You can use TIM models, you can use probably Spacey models, that kind of stuff. So it doesn't matter what the models live, you can always drop them in. And then that's all going to use Lightning under the hood. So what's really cool about Flash is that Flash, normally what happens is you have a baseline and then you're kind of stuck, right? If you want to move from baseline to something that actually you're going to use in production, then good luck. It's going to take you months to like convert the code and everything else. But actually with Ecosystem's Lightning under the hood, you can take that text classifier class and open it up, and it's just a Lightning module. And you can modify whatever you want. And now you're off to the races, right? So I'm showing you an autoencoder just because it's easier to understand, because that text classification one is a little bit more convoluted. But you only need to know a few things, right? So Lightning is, you have this Lightning module, and you basically, you can pass in the models or define the models here. So here I have an encoder and a decoder. I could have also passed them into the model. And then the core of what you're going to do is just training step, right? That's it. So you're going to define the whole thing there. So I'm going to get a batch of data. I'm going to do some manipulations on there to resize it. And then I'm going to run it through my encoder. I'm going to get a Z, so embedding. I'm going to run it through my decoder, and then I'm going to give some predictions, and then I'm going to calculate the MSE loss on that, and that's the loss. And then I'm going to log that loss, and it automatically stream to TensorBoard or whatever loggers you're using, like weights and biases, Neptune, etc. And then you can return the loss from here, and then Lightning will just optimize it for you automatically, right? So it'll minimize it. If you need more control, where you're, like you're doing something very complicated, like maybe you have a GAN or you have multiple optimizers where, they're kind of going in a different order, so you have to retain gradients or whatever, you can just enable a mode which is manual, and then you can call this stuff yourself here, and Lightning will do everything outside of that. So you still have control, but you're able to scale up as well. The third method you need to implement is just configure optimizer. So what optimizer you're going to use for this thing? What are the the parameters, and you return it. So it's very simple, right? Two functions that you need to define. With that defined, then you can define your data at the bottom, and then you just instantiate your model, instantiate a lightning trainer, and then you just call fit, and you pass in the model. You pass in the model, the data sets, the train and validation, and off you go, right? So lightning, there's a training step because that's the training. We're not doing validation here. We're not doing testing. You can do validation step, you can do test step, and it will run another loop, right? So it'll run a training loop for the training stuff, and then it'll run a validation loop for the validation split, and then same for the test. So it splits it up for you nicely. And then you can do it at arbitrary intervals. The beauty of Lightning is that you can do things like, hey, run this for 1 epoch, stop, run it for another 5 epochs, do this, run validation halfway through the epoch, run it at the end of the epoch, run it 10% of the epoch. You can run it once. There's just like all sorts of ways that you can do it, and it just helps your iteration speed dramatically. Lightning is probably one of the fastest growing open source projects today for machine learning. And I put it next to it. It's unrelated, but I just want to show you for kind of the trajectory of the GitHub stars, which is like very aggressive. And again, we've been downloaded over 3 million times. This slide is like, I guess, a few weeks old, but now we're over 500 contributors across the world, best people in the world working on deep learning here. And, I think I want to motivate a little bit about Grid with this kind of story, right? And so the way I think about infrastructure is, like I was in Mexico for a lot of the COVID, right? And I'm from Latin America, so I have family there, and I spent some time there. And I was looking at the roads, and I remember seeing these tracks, right? And I'm like, hey, it's interesting because these are carriage tracks from a few hundred years ago, right? And if you start to think about the evolution of automobiles, for example, you can see that new technology comes out, but suddenly you need infrastructure around it to make it work, right? And so in this case, the wheel comes out on these kind of wagons, and it's not like you can't just take dirt roads, right? It's really hard. And so someone builds infrastructure, and then they build this kind of road to make that process easier, right? So it's these efforts that have to be done across the world when new technology comes out. And, this is kind of the road system 1907. And now you see today that it's much more robust. And still to this day, there are obviously no roads to certain places, but it's more robust, and this will continue. And you see this today with like Tesla, for example, so, electric vehicles. So it's a really great technology. There's range, but there are not a lot of charging stations, right? And so it's not so much about the cars themselves, right? It's more now about the infrastructure around it. It's the same for machine learning and AI. It's not so much about the models themselves anymore. It's really around what do you do with the models, right? How do you train? How do you deploy? How do you get them all to work together? How do you iterate on? How do you debug? How do you, et cetera? So that's really what Grid is doing, right? It's becoming that like infrastructure layer for AI. If you talk about electricity, it's the same thing, right? So this technology was invented, but you couldn't really get access to it at your house. I live a few blocks away from where they started the first electric grid in Manhattan. And, it's only a few blocks of where you could actually get electricity. And then they, invented a few things, and now you could get it, all the way in the north of Manhattan, New Jersey, and then, California, and then the rest of the world, right? And so, so this is the little neighborhood, which is pretty cool. And now today, there's a giant grid, and even today we're still expanding it, right? So infrastructure is never going to go away, but I don't actually think that people need to deal with it. I think that this is our job, right? Like, I think that you guys should be focused on building the models, deploying them, like understanding what's going on with the users, understanding how to build products, making money for your companies, not necessarily like building an MLOps infra tool because it's great. Yes, it's a hard technical problem. Sure, but like, do you want to spend your time solving that and your money, or do you want to spend time actually adding value to your business, right? So that's what we've done with Lightning and Grid as well. And I want to talk about iteration for a second. I mean, I think you guys all know this, but the way that you can be successful in AI is really to iterate very quickly. And the way that that works is you usually have an idea that you start with, right? So maybe let's take vision, and you want to do classification, right? So you're like, okay, well, I have a catalog of products, and I want to figure out what are the labels for these things, or I want to classify when a new, let's say when a new product gets uploaded, I want to basically classify it as this or that. So that's the goal that you're trying to solve. And then you might say, okay, cool. Well, what you should do is start with the simplest model, baseline, right? So you might say, okay, well, let's just take a ResNet 50 and, pre-train an ImageNet and run it on that thing. So that'll be your first idea. That's going to get you somewhere, 60, 70% accuracy, somewhere in there. And then from there, you're going to branch out, right? You're going to have many ideas that go out, and then one of those ideas will work, the other ones will fail, and then from that, you'll branch and continue branching and so on. And this process is going to take you a long time. The problem is that this iteration process is sequential today, right? You cannot paralyze this thing. And that's really what we're trying to do with Grid, is say, hey, you don't have to do this iteration sequentially. You can actually take these ideas and run them all at once. I showed you running a single model, but I don't have to change my code at all. I can add different arguments on that, on the CLI there, to basically spin up 50 versions of a model, for example, with different learning rates and different layers and so on. And so you can really, really start to scale up, to basically endless compute, because, the cloud has way more than whatever you're going to have, even at your corporate cluster. So yeah, I think this is really the key to being able to build really, really fast and quickly. And honestly, when I hear timelines about 6 months, to train a model and deploy it, that's crazy to me. This should take a few days, maybe a week, right? If you have the right tools. So Grid has, like I mentioned, 3 tiers. The community tier, you can try it today. You did, right? So you get access to basically most of the features there. And then, there you're basically paying the AWS cost. That's it. There's no fee on top of that or anything else. So it's just a way to train a lot easier in AWS, but you have a lot more usability. And then, once you start getting into more teams and enterprise features, then you'll have other tiers, right? Depending on your need. If you want to do on-prem deployments, if you want to orchestrate your own VPC, if you want to do things like high-speed data stores because your data sets are giant, if you want to collaborate and so on, and then obviously support. And yeah, we're very flexible with pricing. We work with people, we talk to the sales team, and then they figure out something that works for everyone. So that's all I have. Thank you guys. And I guess I can address questions now.
We had a couple. One is, there's a couple that I'm not sure 100%, in your wheelhouse here, but I'm going to ask them anyway. So one is, can you give an example of how NLP can be used in the finance industry?
Yeah, it's definitely not in my wheelhouse, but I did work in finance and I have worked in NLP, I guess. So I think in NLP and finance today would be a lot of 10K parsing, that kind of stuff. So the reports that companies come out. So the way financial markets move today is information, right? Everything's pretty arbitrage at this point, to where you're not going to algorithmically beat someone. It's about how fast you get information. So when a company publishes a 10K, if you can process it really fast and understand if it's good or bad, then you can make trading decisions quickly, right? There's stuff there. You can also take, NLP sequential models, right? You can basically take those analogies and do that for time series, right? So it's a lot like 𝚃𝚘𝚒𝚒𝚘 for example. It's an NLP model, but it can be used for time series, right? Reinforcement learning is also useful there. Yeah, I don't know. There's a lot of stuff. You're the bottleneck. Your creativity is.
That's a good point. Yeah, true. Okay, and the next question, again, hopefully this is right in your wheelhouse, but how would you train an NLP system to detect something like hate speech on recommender engines?
Yeah, it's a really hard thing to do. Facebook has not even done a great job at doing that, right? You need a lot of data, but the problem is that the hate speech data, it looks very similar. You can tweak words slightly to make it not seem like hate speech, I guess, but when you read as a human, it is hate speech. So it's really hard. I don't actually have an answer for you. Yeah. I think it honestly comes down to
that's a tough one.
Yeah, it's not. I don't think it's
kind of like sarcasm.
Yeah.
William, I wanted to ask a quick question as we switch over. What are the challenges of doing distributed training? I work in a video, so I kind of see it sort of every day. But for the audience, can you kind of highlight, the real challenge that you solved? I think unless you go to do it, then you don't realize how hard it could actually be.
Yeah, it's actually funny because we talked. We have a lot of clients in Grid, and people come with two views, right? They're like, well, I can just build this myself, which is by all means try. Good luck, right? And then we have the people who've already built it and they're like, I really don't want to do this anymore. Please, like, can we just stop doing this? Like, I want to use your thing, right? The challenges around distributed are immense. Like, we've spent years working on this with hundreds of people across the world. It's really about synchronization. It's really about not having any single failure whatsoever, like making sure your logs are all correct, making sure your gradients are synced perfectly, making sure you're not overriding things. It's just so many details that, like, you know, basically you could spend 2-3 years working out just all the details without ever getting to train anything, right? So I think that's really where Lightning and Grid shine is, do you want to, you know, it's great if you want to do the intellectual journey and figure it out, but if you're trying to deliver value and bring something to your companies, then you probably don't want to sit there and, you know, figure out how to do early stopping across GPUs when all your metrics are changing. Do you take the average, the min, the max? Like, what is it? You know, like, it's very complicated.
Thanks for sharing that. Appreciate it.
I know we're out of time. There's a question about latency that I think several people would be interested in your response. So if you have just a minute, if you could respond to that one in the chat, we would sure appreciate it. Thank you so much to William Falcon for talking to us about Grid.ai.
Yeah, thank you.
Great. And let's see. Next, Mark, we have Philipp Singer, that is available to talk to us. Here we go. And then I think we're taking a break after that. And then we have our last speaker, which is Alicia Frame. So we're moving right along. I hope you guys are remembering those 3 objectives that we had for you, which I will put in the chat as you're going through this. So Philipp, thank you for coming to us from 𝚃𝚘𝚒𝚌𝚜. I knew someone named Alauddin Ayadi, and he won Kaggle multiple times, and we were just like not worthy of his presence, and we always thought he was so great. But you are actually a Kaggle Grandmaster, so we're really interested to hear about your experiences. Thank you for joining us at Southern Data Science 2021.
Yeah, thank you for having me. Let me start to share my screen.
We can see it just great. Thank you so much.
All right, perfect. Yeah, so again, thanks for welcoming me. And I want to talk about from Kaggle to industry, or in detail, machine learning strategies for Kaggle versus industry. Before we go into details, let me give you a quick overview of what Kaggle is. Maybe some of you know, probably most of you know, but just to get us on common ground. So Kaggle calls itself your home for data science. It's basically an online community of data scientists and machine learners. And it was founded in 2010, so already quite early in the hype cycle of data science, I would say. And it was then acquired by Google in 2017. And the platform has evolved a lot throughout this time. It is probably most well known for its data science competitions, which is what we will talk mostly about today. But it has many other facets of this community. It has like a full notebook infrastructure similar to Google Colab with CPUs and GPUs. It has this notebook environment. It has a full discussion forum. It has courses, tutorials, and many other things. So it's not only about competitions, but this is kind of the most well-known thing about it. So why am I talking about Kaggle? So my name is Philipp Singer. I'm from Austria, currently living in Vienna. I have a PhD in computer science, also from an Austrian university, TU Graz. Did a postdoc in Germany, and I have quite profound experience in both research and applied data science throughout industry and my current work. And why am I talking about Kaggle? So I'm a Kaggle competitions grandmaster, and I'm currently ranked first on the global leaderboard, which I will talk about in a second. I also work as a senior data scientist at 𝚃𝚘𝚒𝚒𝚜. What are we doing? We are, our motto is that we democratize AI. So we try to enable all people to use and make world-class AI models and applications. Probably some of you know our open source machine learning stack that is very widely used. We also have something very fresh, which is called 𝚃𝚘𝚒𝚒𝚒, which is about building applications, machine learning applications. And we have a huge focus on so-called automated machine learning, which tries to take away many of the machine learning tasks to do it in an automated way. And we have a product called Driverless AI. We are also well known for hiring and employing Kaggle Grandmasters. So we have a Kaggle Grandmasters team. And why am I mentioning this? Because it is kind of the storyline of this presentation, that you try to learn things on Kaggle and try to apply them throughout your work. And we are integrating everything we are learning also while we do and participating in competitive data science competitions in our products and also in the work with our customers. As I mentioned, Kaggle has some kind of ranking system. So when you do competitions, you can get medals. You can get like a gold medal if you're doing really, really well, which is usually something like top 10 in a competition. And you also can get ranking points, which is this kind of competitive measurement then in the end. And as mentioned before, I'm currently ranked first, have like 20 gold medals, have won overall something like 6 competitions. And yeah, that's why I'm talking about Kaggle and industry today. So why are people hosting competitions on Kaggle and what are these types of competitions? This is a screenshot I took a couple of days ago, which has like 8 of the currently ongoing competitions. And you can see, which to me was always the very intriguing part, is that you have very diverse set of competitions. Like the first one here is about predicting stock volatility. The second one is completely different, which is about natural language processing. Third one is about baseball digital engagement. Then we have medical competitions, gravitational wave detection, and even reinforcement learning. So the diversity is very, very strongly given. And this is also important. We will get to that. And why are companies hosting competitions or research institutes? In order to utilize the wisdom of the crowd. If only a small team of people is doing one of these competitions, you're never that challenged and you can never get that many great solutions compared to do if this is done by hundreds or thousands of people. How do these competitions usually work? So mostly they're supervised competitions, so meaning you get presented with some labeled data. And then the goal is to train the model with this labeled data. And then you apply it to unseen test data. And this unseen test data is usually split in some kind of smaller public test data set and a larger private test data set. And the metric is continuously scored on the public test data set throughout the competition. But at the end of the competition, it is scored on the usually larger private test data set, which is the sole data set that then defines your ranking in the end. Let us maybe quickly recap or give a quick overview of how data science projects work in industry. And I know this is not as black and white as visualized here, but be aware that this is kind of a rough setting we are usually in. So if you work in a company and you start a project, there is a lot of business understanding necessary. So you need to talk with the business unit. What is the framing of the problem? What are the actual objectives you're trying to solve? What is the metric? Even coming up with the metric is very important. And you try to gain some business understanding. Then obviously there's this huge part of data. So how can you get the data? And we all know this can be painful in companies. What are the legal requirements? Where can I source it? How can I acquire it? I need to prepare it. So usually we talk about this 70–80% work is done in this area, right? And then also explorative data analysis. And then if you have the data, you can go into modeling. And modeling captures a lot of different things like feature engineering, defining the architecture, doing the training, and very important validation. We will get to that. And then also you want to deploy the model. You want to create an API, you want to do monitoring, scoring, you need to integrate it into products. And if your company is very far with the machine learning strategy, these single tasks are usually done separately by different units even. But in fresh companies, at least I needed to do a lot of these things myself or in my small team. So I needed to do deployment and not a different IT department who didn't know much about machine learning data. So there are many different aspects of a data scientist in industry. And on Kaggle, it has the same process, but a few of the more tedious things fall out, right? You have a competition, you usually get presented with quite clean data, not very clean. So you still need to do data preparation. You need to do explorative data analysis. And you also want to understand the business. This could be still important for feature engineering, for example. But the heavy focus is on modeling. So what type of architectures do I build? How do I train the model? How do I validate the model? And we will mostly talk about these points next. Deploying is not so important, only that you need to generalize your data, your model well to unseen data. And this can be really seen as kind of same thing as in a company, you would want to find good models that generalize well to data in production. The first thing I want to talk about is validation. And I really think this is the most important part and something that you can learn tremendously from if you participate in these types of competitions. And I know that many people do very, very solid validation, but I have seen quite shaky setups. And in industry, oftentimes it is also simplified. So sometimes you only focus on, let's say I have a train, a validation, and if I'm lucky, a separate test data set. But this setup is not trivial. So for example, let's say you want the actual business goal is to apply the model on some unseen new customers. And then people sometimes mix customers in different training and validation folds. And the model learns about the customer and works very well on validation, but it doesn't generalize well because in reality, you want to have a model that works well on unseen new customers. And this is something you learn a lot on Kaggle. How can I build these types of validation setups that allow me to generalize well to unseen data? And you don't want to have any of these types of leaks in your validation setup. And also in industry, you oftentimes have very little comparison to others. You're doing the project on your own, in your own team, right? And you evaluate against yourself. But where do you actually stand? And this is something that is very nice on Kaggle, is that you always have a comparison against others. And a good validation strategy seriously can win competitions. Sometimes modeling is not the important part. I mean, mostly is, but there are definitely a lot of cases where this has not been the critical part in the end. But how are you building a very good validation strategy? Because in the end, you need to select one or two models that work on a private test data set. And here you can see an example. This is like of one of the competitions on the right-hand side, the change from public leaderboard score to private. And the first place was 880 position in the public and shook up to the first spot. So yeah, things like that can happen. And this is a very valuable thing to learn how to do these validation setups. Next thing, obviously, is modeling. In industry, it can depend heavily on the maturity of the problem. If it is a very new type of problem in your company, there is not yet much business value in it. And some simpler models can be actually preferred. Maybe even sometimes, or nowadays, thankfully, oftentimes is that interpretability and fairness are important. And this can be even more important than the score or the objective of the model. So you're fine if you reduce the score a little bit, but have a simpler model that is more interpretable. On Kaggle, all efforts are spent on optimizing the metric. And tiny differences are important. Every digit counts. So here on the right-hand side, again, we can see the top 10 of one competition. And this was an area under the curve score, I think. And the third digit was the deciding one. This is probably not something that is too important in an industry setting, except your problem is already making millions or more. But yeah, so the focus is more on the method side. But on Kaggle, there is no sugarcoating. You actually see what works. If a paper claims they're doing state of the art, sometimes there can be a little like sugarcoating, let's call it like that. But on Kaggle, you can really see which types of methods work across problems really well in a top-notch competitive data science setting. So as an example, efficient nets work always really nicely for any kind of computer vision problem. But with the new transformer computer vision models, they are kind of trying to find their grounds. yet in order to really perform well across settings. Areas of superiority of your solution are, as we already said, validation, in tabular competitions, feature engineering, obviously modeling approaches. You learn a tool stack of techniques, that's very important, and combination of models, blending and ensembling. The next big thing is experimenting, training and inference. This kind of captures nicely to William's talk about Grid.ai, is that in our data science work, it is very important to experiment quickly and fast. In industry, the data size depends very on the problem, as on Kaggle actually, but sampling the data sometimes can be even sufficient in order to get like to the simpler models, and the compute resources that you have at your disposal vary. On Kaggle, you usually have kind of a period of, let's say, 1, 2, 3 months, where you have some certain limited time in order to find the best model. So you need to iterate and experiment a lot. And this on the right-hand side is kind of a visual depiction of one of the experimental phase we had in one of the competitions, where you start with certain experiments, you then decide on, oh, maybe I go this direction with this idea, and then you stop if it is bad, and you need to go back and maybe go a different direction. And this is a very important process. And like logging is important, running engineering is important. I have learned so much engineering stuff on Kaggle to run fast experiments that totally works also then in industry to iterate more quickly. And the final thing I want to talk, and I take this really by heart, is the domain adaptability. Before I go to this example, oftentimes we are working like in a company, which is, for example, in my case, it was insurance company, and we are usually occupied with similar types of tasks, right? I was doing risk modeling, pricing, actuary kind of problems, but you're kind of focused on your domain. And if you read things up, learn things, talk with people, it is always kind of in your bubble of your type of problem and type of data you are working with. And what really bootstrapped also my data science work was getting in touch with different types of problems. And that was my initial like driving point to participate on Kaggle. There were like totally irrelevant competition types, as I shown before. Like we had 8 different types of competitions on this slide. And it was interesting to me because as a data scientist, I think we can work with any kind of data if we understand the methodology well, and if we understand well how to run proper data science experiments and the whole pipeline. The data doesn't matter that much in the end, I think. And I'm picking this competition because it was also one of my favorite competitions. It was more than a year ago already, I think 2 years ago actually. And it was about NFL yardage prediction. So you have, this is like a typical rushing play you can see on the left-hand side. The rusher gets the ball, and at this point of handoff, we had to predict how far is he, or how likely will he be to run that far, like 10 yards, 5 yards, and so on and so forth. And we had given this type of data, like telemetry data. Like on the right-hand side, you can see this type of play. You have the handoff, you know who is the rusher, who are the defenders, who are the offensive players, and then of each player, the acceleration, the direction he is moving, the position, and so on and so forth. And to me, I neither had any idea about this type of data actually, and no idea about NFL. Even though I'm a huge sports guy, I was not being from the US, not into football yet. But it sounded interesting, so we got working with it. And yeah, and to kind of close this already with the final standings, me and my colleague Dimitri, we won this competition by a huge margin. And I'm trying to make this point here, is that oftentimes domain knowledge is not necessary, but can be helpful. And sometimes it can be even, I think, helpful to bring in new ideas to existing problems outside of this bubble. So in sports analytics, usually these types of problems have some very predefined ways of how they are solving it. Like they would, for example, start with the average distance of all the offensive players to the defensive players, and so on and so forth, and would build some more like tabular models. But we found a solution with neural networks and some very custom tailored neural networks that was working really perfectly for this problem. And we advanced not only the state of the art, but in the end, and you can see it here on the right-hand side, this model even found it into production in national television. So here on the bottom, you can see these rush yards over expected, which is kind of, we make a prediction of our model, and they are calculating how much further less far did the rush actually run. And this is kind of rush yards over expected. And they used our model as is in production. And sometimes people say, well, on Kaggle, nothing ever finds its way into production. I think this is totally untrue, because not only does it influence future developments in companies after they are hosting these competitions, and sometimes you even have cases where these models find full way into production. And yeah, to wrap this up, learnings are out of the box thinking is very important. And in this competition, even people used transformer techniques they used for like some graph settings in a molecular competition before, where they were predicting bonds between molecules. So really, I think this domain focus is to go out of this domain focus bubble is a huge learning that I have obtained on Kaggle. And I can reuse these techniques in completely different settings. Final key learnings of my journey on Kaggle, which is now maybe 3 years actively participating on Kaggle, is that Kaggle is a place to learn, develop your own skills, and stay up to date. This is very important for me. The competitive spirit can push me personally forward. I'm aware that this is not for everyone, but even if you're not striving for these top spots, you can learn a lot on the platform. And people are very collaborative, and also usually all the solutions are posted, or the top solutions are usually posted on the forums. Working with teammates is another aspect. You can learn from others. Yeah, try not to be afraid. Just go and try out and get your hands dirty, because there is a lot of interesting data on Kaggle and a lot of interesting problems that you can work off, even if it's already a finished competition. As I said, understanding the problem and data and finding good validation setups that can generalize well to unseen data is crucial. Tackling problems you have little experience is the most rewarding aspect to me personally. Solutions can generalize well across types of data. And yeah, while you participate, you build up a repertoire of methods and techniques. And also engineering is very important. At least that's my strong point, and an important part of a good data scientist. With that, thanks for listening, and happy to answer any questions.
Fantastic, Philipp. I'm so excited because I've run competitions myself, once for Microsoft, several times for Georgia Tech, ran one for University of South Carolina, run them for the Athletics nonprofit that's around social good. So I'm a big believer in these sorts of things. And I love that you highlighted so many advantages. You learn new techniques, you get to work with new people, you work on interesting data, different problems. Such an awesome talk. So a couple of questions for you. There was a question around, I mean, especially because you're in such a fast-paced environment and you got to get this thing done. How do you decide on your technique? Do you have like I sort of have like a toolkit, and I use almost like a decision tree. But how do you quickly decide on an analytics technique that you're going to apply?
Yeah, I think this is a lot of experience, I would say, right? If you have participated and done a lot of different data science projects, you go to a new one and you already kind of see how things are connected and what type of direction you go. And I think many of the top Kagglers and top data scientists, they get a faster head start because they already know, like, oh, I will start with this, and this problem sounds similar to that one, and I will go this direction. And I think that's also like this point that I try to make with different types of data sets that you work with. You kind of are able to puzzle things together at some point. And you learn
Yep.
method and method. In each competition I do, I learn something new that I'm trying to apply post-hoc in new competitions or new data sets or new problems I'm working with.
Yeah, I would imagine too that that's well put, Philip. I would imagine too that the more you do, the more widened your toolkit gets. And I imagine during the framing process, you're probably thinking like, oh, this is definitely a grouping thing. I'm going to use latent class clustering, or this is definitely a, you know, and the question was specifically from one person around neural networks, you know, and how do you know when to use those or not? But it sounds like really it's just based on experience and things that have worked in the past.
Yeah,
Very cool.
maybe one thing to add. I mean, as I said, there's a huge community on Kaggle, and even in competitions, you usually have very quickly some kind of baseline models published. You have some starting solutions, and you quickly see in what kind of direction the whole thing goes, even if you yourself would not know. And you can always follow up. Like it has this notebook infrastructure. People are sharing notebooks that you can run and get a baseline submission in and get a baseline model in. So it's not it's not that you have to start yourself. There's usually very quickly a good way to look at what others are doing and start with that.
Fantastic. 3 other questions. I know we only have 4 minutes, but we'll try to be quick here. How do you think this sort of thing prepares you for the real world? Like if you're trying to transition, you're in the middle of a doctoral program or a master's program, or you're just trying to get a new resume in line and benefit in many other ways. But how do you think this would prepare you for the real world, especially given that most of these are somewhat cooked? The data's perfect, business question is fairly well formed, that sort of thing.
Yeah, I think the data is not always perfect, but yeah, as I mentioned in the beginning, it is kind of definitely better utilized. And I tried to picture this with like what parts of the data science pipeline it covers, and it covers mostly the modeling part, definitely. Like also what do I do with the data? What type of feature engineering do I do? What type of modeling? How do I apply it? How do I experiment it? So the actual data science work, if you want to call it like that, is something you learn on Kaggle. And
love it.
Yeah.
So your chart of the process with the problem and the framing, I love that you didn't forget about framing. That's awesome. I actually encourage people in chat, like, please take a picture of this, but that what you're trying to say, I think is, or what you did say is that you're not necessarily going to get great experience in every single aspect. That it may be that you get more experience from the modeling side and the data science portion of a Kaggle competition, but it might not necessarily make you a perfectionist on problem framing. Very, very good point.
Yeah, absolutely. Yeah.
And the last 2 questions, so there's the forming, storming, norming, performing, group dynamics, and how teams tend to work together. There's like these 4 stages. In a Kaggle and other competitions, you have to work very quickly, and a lot of times it's with people you don't even know. So how do you manage the teams dynamics, and especially like when it comes to conflict?
Yeah, I mean that's always a difficult topic, right? You can have interpersonal conflicts all the time in any kind of team environment you work in. I mean, I love teaming up because I also learn a lot from others, and you learn whom you can work well with, right? And then you're trying to stick to these types of people. Obviously, as a fresh starter on the platform, it is kind of tricky, right? You have no reputation. Who really wants to team up with you? So the best thing to do is to do well, show contributions to the community, engage in discussions. Don't always be blinded by these public leaderboard scores. Really try to identify who really brings value and whom you can learn something from. And yeah, then
awesome.
It can be always hit or miss. It's never that easy.
That's great advice. I love it. Okay, and then lastly, what do you think is the biggest challenge? Because there's so many things that you have to, sort of get right. I mean, again, I'm like your fan right now because I'm really in awe that you're a Grandmaster. So what do you think is the biggest part? There's the problem framing, there's working together, there's the fast environment, there's the need for flexibility of tools, there's the storytelling at the end. Like, what do you think is the biggest challenge in these competitions?
The biggest challenge, it's very hard to say. Like, it can also be very different from type of problem. I mean, the biggest challenge is, as I said, these types of competitions are very competitive, and you can hit type of a barrier at some point. And you have your tool stack, you have your ideas, and then you suddenly stop and you can't progress further. And breaking this barrier is actually where you learn the most, I think. And going through this next step in order to improve your solution is what really then also drives me. And I think where a lot of learning comes into play, because there you need to start learning new things. And yeah, so not getting frustrated, really also enjoying it. This is very important, because it's a fun process, right? You're doing very interesting data science problems, sometimes, or thankfully even quite regularly for goods. So yeah, enjoying the process and don't get frustrated and really try to push the barrier. That's what motivates me also.
I love it. Thank you. We did forget about saying to have fun, right?
Yeah.
It's a learning experience. That's awesome. Thank you again so much to Philipp Singer, Kaggle Grandmaster, for talking to us about competitions at Southern Data Science Conference 2021.
Thanks.
All right, welcome back, everyone. Hopefully you had a good break, and I'd like to welcome our next guest, Beverly. Go ahead and take it over.
Oh, sure. Thank you. Welcome back, everybody. I enjoyed seeing what you had in our chat as far as what you learned so far, and I'm excited about what Alicia is going to share. I personally think that graph analytics is going to be kind of the next big thing. How we started talking about machine learning, and so it could be quite a big deal. I'm excited to hear what she has to say for us. And so, Alicia, thank you for joining us for Southern Data Science Conference 2021. I will let you take it away.
Let me just share my screen. There we go. And so today I'm going to be, everybody can see it? Awesome. So today I'm going to be talking about graph data science, and really, what the heck is it? How do you get started? What's it good for? How do you do it? I think people talk about graphs and data science a lot. It's a hot topic. But when people say graphs and data science, they could mean anything from graph algorithms, network science, to graph neural networks. And so I'm from Neo4j. We're kind of the graph company. And I'm going to be talking about kind of what is graph data science? How do you do it? What's it useful for? How do you get started? So folks who aren't familiar with Neo4j, we were the creator of the world's leading graph database. And what that means is storing your connected data in a connected shape. So just like a relational database like SQL stores your data in rows and columns and tables, we store your connected data in a graph. We introduced the world's first graph data science platform for enterprises, which is mostly what I'm going to be talking about today. Basically, graph techniques that you can apply to your connected data. We also introduced the world's most flexible graph data model with the labeled property graph, which is kind of how we represent data. And I'm going to talk more about that. And we introduced the world's easiest to use graph query language with Cypher, which basically lets you define kind of the patterns you're looking for in your connected data, and then quickly pull back the results that match those patterns. And Neo4j is used by thousands of companies across tons of different verticals. We're not really like a use case specific platform. We've got folks who use Neo in retail, in banking, in life sciences, in tech, you name it. If you've got connections, folks are probably using a graph database. So before we dive into graph techniques and how do you do it, I kind of like to start off with level setting on what's a graph. And you hear people talk about it. And I know in data science, we often use the word graph to mean like a bar chart or a histogram. So when I'm talking about a graph in Neo4j land, what we're talking about is a labeled property graph. And so what that means is you're representing your data as nodes and relationships that connect them. And the easy way to think about this is a node is a noun. It represents an entity in your graph. In this example, we've got people nodes and car nodes, right? They're things. And then there are relationships that connect them. So a person can love another person, a person can drive a car. And then those nodes and relationships can also have properties on them that describe them. So a person node can have a name or a Twitter handle or a birth date. Your relationship, your drive's relationship has when they started driving the car. So if you start thinking about representing your data that way with nouns and verbs, and you can have properties, you can start to think about how you can build up this really rich, true to life representation of your data sets. And if you start to kind of think about things this way, you realize that everything is really naturally connected. And I think often when people talk about graphs, there's this trap of thinking about graphs as like social graphs, right? We all used Facebook, LinkedIn, and you think about, well, a person knows another person. And this is where a lot of this work really started, right? You have networks of people, you might have employers or suppliers, and you have looking for who's a friend of a friend, right? But that's kind of just the beginning of graph. You can build on that and think about your transactional graph, where you have people buying items, returning items, looking at items in stores, or people making bank transfers with other people. And you can start to use this for things like risk assessment, who's committing fraud, what might someone buy next. But really, when you think about graphs in their most generalized format, this is really a knowledge network or a knowledge graph where you're just connecting heterogeneous concepts. So nouns and verbs connecting really diverse data sets and concepts in a true to life kind of whiteboard way. And you can think about this like master data management, enterprise content, kind of domain specific data. In my little toy example, I have a person likes a sport, they're a fan of a team, they live in a country, someone else is a player of that sport and plays for a team. And you can start to connect really different concepts in this single graph representation. So you can analyze everything in context. And what's really cool about graphs is the structure of your graph, how those relationships connect nodes can be really predictive. And I like to kind of use this generic example of everyone knows the saying that it's not what you know, it's who you know. Like when you say, how did you get your last job? It's not, what was your degree? How many years did you study? What did you do specifically in your last job? It might be, your mentor in college helped you prepare for an interview and introduced you to someone they knew at a company. It might be your former coworker left for another company, introduced you to one of their friends who told you about an opening, right? It's these connections that predict the future, not just your rows and columns. And what's really cool is like everyone knows that saying, but it's actually true. There are academic papers that bear this out. So if we go back to our graphs of people and you want to say, how do I predict who's going to get a pay raise or a promotion? It's actually that social structure that's predictive. If you look at that global topology of the graph, that structure of your graph predicts who's going to get a raise, who's going to get a promotion based on kind of where they sit. So people who are in structural holes or kind of organizational misfits, and we'll talk about how you would measure that, are more likely to get raises and promotions than those who aren't. So this is a case where in the real world, relationships, those connections are predictive. And if you think about it, connections are really what drive businesses, right? It's not just the numbers, it's the connections between them. So if you start thinking about your nodes, those nouns, you have employees, customers, products, parts, plants, warehouses, suppliers, partners, regulations, right? All of these concepts, but they're meaningless without the connections between them. So this employee works in this department. This customer bought this product, which came from this warehouse. The connections and the relationships between those concepts are what predicts or explains what's going to happen next, what's happened in the past, what's important, and kind of where should you start paying attention. And really, I can't underscore this enough, relationships, topology, it's a really strong predictor of behavior. If you're looking for like a fun beach read, weekend read, James Fowler's Connected is a really cool kind of popular science book about the power of relationships. And they give some really nice examples of how predictive relationships are. If you want to predict who's a smoker, probably all of us, if you said, how do you predict who smokes? You'd be like, okay, how old are they? What's their gender? Where do they live? How much money do they make? How much education do they have? Those would not be your most predictive features. Your most predictive feature would be how many of your friends are smokers and how many of your friends' friends are smokers. Similarly, if you said, I want to predict who's a voter in the next election, it's not people's demographic data, it's not their income. It is how many of their friends and family members are voters and how many of their friends' friends and their family members' friends are voters. Those relationships are the strongest predictor of what's going to happen next. The problem is, and this is kind of where graph data science comes in, is you can't analyze what you can't see. And so most data science techniques are built around tables, rows and columns. And you can't, it's really hard to get relationships, those connections between your rows into your columns, right? And you can kind of manually engineer things. You can hand engineer a couple predictive features. If you know specifically the relationship you want to analyze, you could probably pull that out. But the difference with graph is graphs are built on relationships. So you're not guessing at the connections, the correlations. They're there. They're treated as first-class citizens, and you don't have to guess anymore. You can analyze them because they are on par with your nodes. So you can see them, you can start to make sense of them. So this isn't just Neo4j making up new uses for graph databases. This is kind of a trend across the board. And probably some of you who are like, yeah, graph data science have heard about us or these techniques from industry analysts like Gartner. So in their big trends for data science and analytics, they said that graphs form the foundation of modern data and analytics. And they highlighted that graphs can improve everything from the predictive accuracy of your machine learning models to explainable AI to user collaboration. And they found that, as organizations get more mature, they're much more likely to adopt graph techniques. And they feel that graph techniques are one of the biggest trends for this year and the coming decade. But it's not just industry analysts, right? It's also academic research. So this is one of those exciting things where you've got analysts, you've got software vendors, and you've got academics all really excited about something. So if you look at just academic publications about graph, they've been growing almost exponentially. If you go to 2010, 205 publications. Last year, nearly 6,500. Academics are kind of leading the charge in using graphs to better describe data, to accurately represent data, and to make better predictions. And at Neo4j, we've seen kind of those same statistics borne out. If you're like, I'm ready to get started, I don't want to hear the rest of the talk, we have a really cool book called Graph Algorithms, Practical Examples with Spark. We've seen over 200,000 downloads of that book. We've seen a massive increase in interest, traffic on our page, community engagement, and just data scientists engaging with graph. So it's really cool that you've got industry experts, academia, and software all kind of coming together to help you make sense of relationships. So I've been talking for a while. Hopefully you're like, okay, I think graphs are predictive, but you're probably still wondering, what do they have to do with data science? And I like to kind of step back, and if you think about data science as answering questions with data, right? Doesn't matter what you're trying to do. Data science is just using the data to answer questions, get insights. Graph data science is just using the relationships between your data points to answer questions. So not just looking at nodes, not just looking at rows and columns, analyzing relationships. And then you can kind of break graph data science down into three pieces. You've got queries, where what you're doing is you're looking in your connected data to find the patterns you know exist. So I mentioned in the beginning, Neo4j is originally a graph database. How can I find patterns I know are important? I'm a domain expert. I know this pattern is highly predictive. I know this pattern is important for my analyses. So maybe I'm doing fraud detection, and I want to say, how many people committing fraud are in this transactional graph within 3 hops of each user as a predictive feature? So it's all about finding the patterns I know exist. Then you can talk about applying machine learning. And this is, maybe you have labeled data, maybe you have unlabeled data, but you want to say, what's important? I have too many connections. I don't know where to look. I can use graph algorithms, which are unsupervised techniques, to figure out what's important, how are things clustered, what's unusual in my data. Or if I have labeled data, I can start to make predictions about how my graph will evolve over time. or missing data in my graph. So maybe I want to predict who's going to buy what next based on my graph topology. Or maybe I want to predict who's going to churn. If that's a node label, a noun in my graph is churner, maybe I want to predict who's going to churn. And then finally, you can use visualizations. And these are kind of the bow on top of everything, right? Graphs are cool. They're useless if you can't explain to your colleagues what you're doing. And so visualizations are all about kind of exploring, understanding your results, sharing them with your team, collaborating, explaining. And so if you put those together, this is all the different ways you can use graphs and relationships and connections to answer questions. And if you really want to think about like, how do I get started? It's not that hard. I like to think about it kind of like increasing complexity steps where there's value at each step. So you kind of start with a knowledge graph that's getting your graph data in a graph shape, where you can start to run queries to find the connections you know to look for, to confirm what you're trying to find the patterns you know are important. But once you've got that knowledge graph, maybe you don't have any labels. The next step is you can run graph algorithms, which are basically network science techniques that are unsupervised. You can find patterns, trends, anomalies in your data. But then once you've maybe started to add in some labels, maybe you know what you want to predict next. That's when you can start doing graph native machine learning, where you're learning about the structure of your graph, predicting how it's going to change in the future, predicting what data might be missing. So that might seem super complicated and intimidating, but really you start with getting your data in a graph. You kind of learn to crawl with some graph algorithms to help you figure out what should I be looking at. And then you walk and run with your graph embeddings, your graph neural networks, your supervised machine learning to predict what's going to happen next. So cool, how do you do this? I'm from Neo4j, so I'm going to talk about how you do it with our software. We actually have a framework for graph data science. And so at the heart of that is our database. So you store your connected data in a connected shape. On top of that, you run the graph data science library, which is what I work on, which is basically an add-on to the database that lets you do data science on tens of billions of nodes, tens of billions, hundreds of billions of relationships, start to understand the patterns, the anomalies, make predictions about your graph. And then when you want to visualize or understand what's happening, you can use Bloom, which is specially built graph visualization software. And what's really cool is this is all free, open source. You can get started, pick it up today. And so I work on graph data science. And so what can you do with the graph data science library? There's really two pieces. The one that most data scientists think about, and if you say like, I want to do GDS, people are thinking about graph algorithms, so unsupervised techniques, and machine learning methods. And we offer all those. And this is about computing metrics about your graph, understanding connectivity and topology. So are highly parallelized, really built for scale. And my team spends their time implementing the right algorithms to answer your questions. But then the other piece of it is all of the tooling in the analytics workspace to take that transactional graph that you've built up, your knowledge graph, and transform it into the right shape, optimized for doing data science, or to help you transform it into different shapes and layer those together for different projects. So maybe you have a knowledge graph of people, places, things, but for this data science problem, you want to actually just look at people who looked at the same places. How do you transform your graph into the right subset? How do you mutate it in order to do the algorithms that you want to run quickly? And so taken together, we offer both tooling to do data science, but also kind of the ecosystem tools to run at scale, reshape your data, experiment, and get your results into production. And so if you look at what you can do data science-wise, it breaks down pretty simply into unsupervised techniques and supervised techniques. Just like you've probably seen versions of this chart in many places. In Neo4j's graph data science library, on one hand, you have unsupervised graph algorithms. Right now we have, I think, around 65. And what these are is I don't have labels. I want to understand what's important, what's going to happen next. Is there a path between A and B? How do I reduce the dimensionality of my graph? This is the unsupervised techniques. And then on the other side, we have our supervised machine learning techniques. And we've actually introduced these in the last probably 6 months or so. And what we have here are techniques that use your graph as your labeled data to make predictions about where relationships will form in the future and where predict missing labels, assign labels that might be missing from your graph to classify your nodes. I'm going to walk through each one of these and talk about what you can do and what we offer. So in terms of algorithms, we have 6 different categories to answer kind of 6 different types of questions. We've got pathfinding and search. And this is really about, if you've thought about graphs before, you've probably thought about pathfinding algorithms. This is shortest path, route availability, what's the optimal path between A and B, how many paths are there? And usually you're using this to answer kind of supply chain and logistics questions, risk assessment questions, pretty typical graph questions. Then we've got the centrality and importance algorithms. What these are is they use different features of your graph, different ways of defining importance. And these can tell you for each node in your graph, how important is it based on its relationships, its neighbors, neighbors, its structural role. And you see these used in everything from marketing, like who should I market to risk assessment of if I've got a telco network and this node goes down, am I going to have an outage? We have the community detection algorithms. And what these are is they basically tell you, where is my graph clustered? So if you've done k-means clustering on tabular data, and you think about a graph, this is just which parts of my graph are more densely connected to each other than the rest of my graph. And there's different techniques for this. You might be familiar with something like Louvain. It's often used to find things like fraud rings, really useful techniques. You see it used for like market segmentation, fraud detection, all kinds of use cases. We've got the heuristic link prediction algorithms, and these are unsupervised. What they do is you basically define rules about where links should form, and then we'll give you the probability that a relationship should be there. We have similarity algorithms, so you can say, given 2 nodes in my graph, given their properties, given their neighbors, given the graph topology, how similar are they? And so if you want to do a recommendation, maybe I want to make a recommendation based on the most similar customer in my graph. Or if I'm doing fraud prediction, maybe I'm doing that prediction, who is fraudulent, based on looking the most like a known fraudster. And then finally, we have graph embeddings. And these are basically dimensionality reduction techniques. Everything else I've talked about, these all basically, you have a formula, you apply it, you get a result. The graph embeddings learn from the structure of your graph, a representation of each node in your graph, custom to your problem and your use case. So you use them a lot for, okay, I've got a 5 billion node graph. I cannot just put this into my machine learning pipeline. What am I going to do? 5 billion by 5 billion adjacency matrix, mostly zeros, really sparse, can't make sense of it. Use the graph embedding to develop maybe a 250 number long representation that encodes everything important about your graph in a machine readable representation. And so this is all basically techniques where you don't know what you're looking for yet. You're trying to figure out what's important. And maybe you use some for analytics where I say, I want to identify the most important nodes, or feature engineering where I want to summarize features of my graph to put into my pipeline. And so this is where we kind of switch gears into the supervised ML. So on the one hand, you can do predictions influenced by graph structure. This is just your traditional existing ML pipeline, but you think relationships are important. So what you're going to do here is you've got your data represented as a graph. You're going to run some graph algorithms to come up with some graphy features. Maybe each node in your graph is a row. You're going to run PageRank between this centrality and node to vec, and then those become new columns in your data set to make a prediction. And your prediction is something influenced by graph structure. On the other hand, you can make predictions about the structure of your graph. And what you're doing here is you're enhancing your graph by predicting what's going to happen to your graph in the future, or what data is missing from your graph and kind of filling it in. And so in Neo4j, we talk about 2 types of in-graph machine learning. One is node classification, where you're saying, what kind of node is this? Maybe I have a banking graph and I have some nodes that I know are innocent, some nodes that I know have committed fraud, and some nodes that I don't know about. I can use those labels that I have to classify my unknown nodes based on the structure of my graph to say, what kind of node is this? So I'm using my graph as my labeled data. Similarly, we talk about link prediction. And so this is, I have my graph, it's got some relationships in it. And either there are some relationships missing, or I want to predict what's going to form in the future based on the relationships that exist in my graph and the relationships that don't exist in my graph. Those are my negative examples. And so here, maybe this is a transaction graph of people and products, and you want to predict a future link between a person and a product because it indicates what they're going to buy next. Or maybe you have a biomedical knowledge graph. You have genes, chemicals, and diseases, and you want to predict a new link between a gene and a disease that hasn't been discovered yet, but it's real, and you might use that for developing a future drug. And so in this case, what we're doing is we're using the graph structure itself to make predictions about data missing in the graph or what's going to happen next. And so this is supervised ML in Neo4j. And so kind of wrapping it up, what you can do to kind of get started with graph data science in Neo is we actually offer a completely in-graph machine learning workflow. So you start with your knowledge graph, your data, your connected data in a graph shape. You can start running graph algorithms for feature engineering. So I run those PageRank, graph embeddings, clustering algorithms. Then I use those as features to train my predictive model, which I can store in my Neo4j database. And then I can apply that model to my existing data if I think I have missing labels or missing links or new incoming data. And then I can use those predictions to make better decisions, enhance my graph, or just save those models, publish them, share them with my team. And so just to kind of wrap up, graph data science is all about using connections to answer big questions. Connected data is really powerful. Your nodes on their own don't mean anything without the relationships between them. And graph data science is just how you leverage those relationships to make better predictions with the data you already have. And you can start saying, what's important to my business, what's unusual, or what's going to happen next. And I'm happy to take some questions. And if you're curious and want to get started, we've got books you can check out. We've got videos, we've got white papers. I did not do a demo today, but if you want to grab some code and take a look at it hands-on, you can check out my GitHub repo. Thank you so much.
Fantastic. Thank you, Alicia. Can you put your GitHub repo in the chat, if you don't mind, so that way people can have it in real time?
I can do that.
Awesome. We do have a couple questions. One is, are there any use cases for graph algorithms in manufacturing, smart grids, or the energy industry, which is where I spent the majority of my time when I was on the practitioner side. So I love the energy industry. Can you tell us, aside from the more obvious optimization, are there other use cases you can think of in that area?
Yeah, so I think we've seen a lot of use cases. Kind of the classic ones are your risk assessment use cases where you say, I can represent my network as a graph, and I want to know what's the most vulnerable node in that network, where maybe I want to add some further redundancy or change my practices or monitor that more closely. And that's kind of typical graph algorithms. Other use cases we see are kind of anomaly detection, where maybe you have a network and you want to know, it's got millions of nodes in it. You want to know if your network has been penetrated by a bad actor. You want to know if something's going wrong. And you can run your algorithms to basically say, here's my network in a normal state. I'm going to monitor it and see if it's in an anomalous state. And if I notice a certain deviation from my previous state, I'm going to follow up. And then you can this is all unsupervised techniques, right? I'm going to run an algorithm, get an answer, kind of classical analytics. Risk assessment is I'm going to look at, how many paths are there between A and B. I'm going to look at betweenness centrality. Anomaly detection is, community size, centrality scores at different nodes, graph embeddings. If you move into the predictive space, it might be looking at, I want to predict the next outage in my network. And I have historical data where I've got, this node in my graph has gone down. I want to use the topology of my graph to predict what'll go down next. And that's kind of a node classification use case. Or if it's
very nice.
Sorry. Yeah, there's so many things you can do.
So many. I know. Yeah, I was thinking about a time that I was trying to predict brownouts. Like blackouts, you can sort of start to get a better propensity. And then when the electricity is flowing, it's all good. But brownouts are really hard to predict, and how much graph would have helped me back in those days. So very nice. Okay, the next question is, it's very interesting. You think about, when we talked about graph, we're thinking about like people, or we're talking about objects or something like that. But what about text? You know, and making the connection between certain types of phrasing and words and things like that. And so I've seen this in a legal context. The question is about how can it be used to find similarity between medical reports based on something like a self-developed dictionary?
So there's a couple different ways you can do that. And this comes up from time to time. And the first thing is like, how do I develop my graph? And a really common use case is, you use NLP to find subject verb object relationships, to find syntactically linked pairs, and you build your graph from that. Or maybe you have document embeddings, right? Where you've run doc2vec, you've got a numerical embedding for every document. And then you use something like k-nearest neighbors graphs, maybe cosine similarity, to build a graph from those numerical embeddings. So you can say, oh, hey, this document looks like this document because the embeddings are similar. But what's cool when you're using KNN is it basically creates a graph from tabular data. So you could say, well, here's the most similar, the k nearest neighbors of this document. What are the 2 hop neighbors, 3 hop neighbors, or run community detection and say, which community is it in? And so you can kind of start to build increasingly elaborate data sets on top of that.
Very nice, very nice. We may have 2 more questions, but I asked for clarification on one, so I'll go ahead with the other one. But while talking about node classification and telling what node it is, in Neo, if I'm that node, does it tell me if I'm fraudulent?
Depends what data you've got. So if you've got a data set that you've loaded into Neo that has accounts that are, each node is an account, and they make transactions between accounts, and those are your relationships. Some nodes are labeled fraudulent. They've been known to commit fraud in the past. Some nodes are labeled innocent. You thought they were committing fraud, someone investigated them. Nope, they're fine. So then you can predict for these unlabeled nodes, or these nodes I'm curious about that I haven't investigated yet, how likely are they to be committing fraud? How likely are they to correctly have the is fraudulent label? I think if it can predict whether you are committing fraud, I think you are probably the best answer of that question.
Very nice. Thank you, thank you, thank you. And right on time. I appreciate your presentation and for being here as part of Southern Data Science Conference 2021, Alicia Frame. And also big thanks to Neo4j for sponsoring this event and making it possible. Thank you again.
Thank you.
Next, I'm going to close this out with an announcement. There was a competition that was run recently. And so if you are one of the winners, I'm not sure if you can share screen or not, or share camera, but if you can share camera, I would love it if you would do that. But I'm going to share my screen here, and we're going to announce a few winners, and then I'll have a few closing remarks for you. Cool, cool, cool. Okay, there is an organization called Atlytics, and some of you may have heard of it, especially if you're in the Atlanta area. It's Atlanta Analytics for Community Service, and I'm one of the founding members of Atlytics, along with Khalifa Al-Jada, who's the brains behind this whole initiative of Southern Data Science Conference. And then we have a third colleague named Andrea Popescu, and we were the founders. Also on our board, aside from the founders, is a very hardworking, intelligent, and wonderful colleague named Julie Grantier, who I believe is on the call right now. So Atlytics, as an organization, it leverages data science for good, Atlanta Analytics for Community Service. And Atlanta is really more focused on where the resources have traditionally come from and where we're founded. But what we envision is a connected analytics community aware of how it can benefit society, right? What is it Spider-Man's uncle said, that with great power comes great responsibility. And I think data science is a superpower. So we try to use it for good. We leverage volunteers to help us in that endeavor. This is our board of directors that I just mentioned. Andrea, Khalifa, and I are the co-founders, and Julie Grantier is our hardworking fourth board of directors member. Okay, the hackathon. This hackathon is called Analytics Data for Hope, and we've had multiple Analytics Data for Hope hackathons in the past, and it takes a village. So this team, headed up by John Tardy, was responsible for letting the open community know about the hackathon and what they needed to do in order to try to win a prize and get the experience from participating. Mary Pat and Husafa were also on John's team for helping to make this hackathon a reality. The business question that the hackathon team was faced with, or teams were faced with, is around affordable housing. There are very big challenges, especially in the Atlanta area, where housing affordability is one of the most difficult things that our major cities are facing today. And so Mayor Keisha Lance Bottoms has made it a top priority to work on affordable housing. So we decided that this was a great place to start. So drum roll, they already know that they won, but I want to make sure I announce these teams. We had a first place winner, and that was Team Philipp Phoenix, which was Darlene Phoenix and Carla Manoy. Not sure if I'm saying your name right, Carla. And their main takeaways are listed here. I won't read them to you. So congratulations to Darlene and Carla. The second place was Bahadat, Shashank, Muntaser, and Elena, where they came up with some great solutions and takeaways to our business challenge. So thank you, 4 Musketeers, for your participation and all your hard work. And then our third place winner was Awesome Effects, which was Annie Lu, Xin Yu, Fan, and Tao. And their biggest takeaway was a large percentage of single parent households are in need of rental assistance. And they were able to analyze the data and find out what's the degree of this need and that sort of thing. So congratulations, huge congratulations again to all of these teams that were involved in Analytics Data for Hope. We're very, very pleased that not only are we interested in learning a new skill, collaborating with colleagues, but you did something for good. You actually benefited the community through data science. So you may not have had to grab a shovel and start digging or knock on a door or anything like that, but hands on keyboard, working together to leverage data for community betterment. So thank you again to those teams. Mark, do we have the ability for them to for them to camera share, if that's an option, or are they not able to do that?
Yeah, I'll have to pull them on if you want to pull up the names.
Ah, okay. There's not like a magic quick button.
Oh, unless we
to do that.
promote everyone.
Oh, gotcha. Well, okay, but they can still talk verbally or no?
I'll do them one by one, actually. Not the most efficient process.
Yes, probably not. Darlene and Carla, are you guys available? Are you on the call? If so, I think they can only talk to us via chat. Oh, Darlene is there.
Yes.
Yes, Darlene. Oh, great.
Hello, can you hear me? Yeah, I'm here.
Yes. Well, huge congratulations. What did you think was the most challenging part of the hack?
I think it's really like identifying what to focus on, because when we were looking at the data, it's very easy to get overwhelmed by the amount of data that's there. So it's really just trying to narrow down on what we want to answer, and then going with it. Because otherwise you would go in different directions and not finalize on what problem you want to answer. So it's the data framing aspect. Yeah.
Yeah, because we do tend to go down some rabbit holes when we get excited about the data or it's using a certain technique. And then the second team, I think I saw Bahadat. I don't know if Shashank or any of the other members are on, but if you're available, if you could unmute and just tell us, what do you think was the most rewarding part of this hack?
My name is Bharat. Can you hear me now?
Yeah, we can hear you.
Okay. And I think the most rewarding thing is just the possibility that this information could actually help improve people's lives.
That's great. Thank you so much. And a huge thank you again to Southern Data Science Conference, and more specifically, Khalifa Al-Jada, for helping with Athletics, making this possible and allowing us to congratulate the winners of the hack during the Southern Data Science Conference 2021. In closing remarks, before we move into the, I'll let Mark cover the logistics and things like that, but before we move into that, just real quickly, thank you for being here. I know that you had to take time out of your busy schedule, not just professionally, but even socially, because it's been on a Saturday. I do really, truly hope that you've taken away, pieces that I talked about, which I hope you have a renewed interest. I hope you feel stimulated about innovation. I hope you're anxious to get back and try new things. I hope that you're going to dig into some of these decks and look at the recording. And I have so much hope that this is going to help you to sort of catapult where you are now and move forward with data science and elevate this practice that we all know and love. So thank you again. I've been in data science since 1991. Back then it was called something else. It's what I've liked. It's always going to be what I like. And I'm very happy to have such a wonderful community. And thanks for having me as part of Southern Data Science Conference 2021. Mark?
Thanks very much, Beverly. Appreciate you sort of driving today. And everyone, we're about to head into the networking event. If you need to take a quick break, definitely feel free to do so. So once I end this meeting, the networking event will begin. You can go to the Eventbrite page to get the actual link. I'm going to post the link in the chat as well. And hopefully all of the lessons that you've learned, you can take to either go get a job in data science or, progress up the ladder, so to say, and ultimately drive more business value wherever you work, or if you're a grad student, graduate a little faster. So check the chat for that Zoom link. It'll only activate once I close this meeting, which I'm going to do pretty much any time now. And once again, thank you very much for spending your Saturday with us. And we deeply appreciate it.